Look up at the night sky. What do you see? Pinpricks of light, familiar constellations, the gentle arc of the Milky Way. But beyond that serene canvas lies a universe of breathtaking chaos and mystery, places where the rules of reality seem to bend and strange new wonders emerge from the darkness. Today, we're traveling 300 million light-years from Earth to one of the most fascinating sights in the known cosmos, the Mice Galaxies. Officially known as NGC 4676A and B, these two spiral galaxies are locked in a beautiful, destructive dance, a cosmic collision unfolding in slow motion. And within that chaos, something extraordinary is happening. Strange objects have been detected, things that defy easy explanation and ignite the imagination. From bizarre stellar remnants to unexplained energy signatures that some researchers whisper could be signs of technologies built by civilizations beyond our own, this isn't just astronomy, it's a treasure hunt. And you're invited along for the journey. Think about that for a moment. 300 million light-years. It's a distance so vast our minds can hardly wrap around it, and yet there it is, a pair of galaxies swirling and merging, giving birth to stars, tearing others apart, and creating environments unlike anything we see in our own quiet corner of space. This is where the strange becomes normal, and the normal, well, it just doesn't exist here. Over the course of this video, we'll explore 30 of the most peculiar objects ever observed within the Mice Galaxies. Some are natural marvels, cosmic accidents that challenge what we know about physics. Others make us wonder if we're truly alone in the universe. This is a story of curiosity, of humanity's relentless drive to understand the unknown, and of the awe that comes from staring into the depths of space and realizing how much is still left to discover. So settle in, let your imagination run wild. We're about to dive into one of the richest astronomical playgrounds ever observed, a place where every strange signal, every anomalous reading invites us to ask bigger questions. What will we find? What might these objects tell us about the nature of reality or about other life among the stars? This is more than a tour of strange sights. It's an exploration of wonder itself. And it all starts right here with 2 galaxies and 30 mysteries waiting to be uncovered. Our journey begins not at the edges of this cosmic collision, but at its very heart, where the most fundamental and fearsome forces in the universe are at play. Deep within the swirling cores of NGC 4676A and B, astronomers believe a breathtaking dance is underway. Each of these spiral galaxies almost certainly arrived at this merger with its own supermassive black hole, an anchor of incredible mass at its center. Now, as the galaxies intertwine, these 2 gravitational behemoths are finding each other, locked in an ever-tightening orbit, a true supermassive black hole binary system. Picture the sheer scale of this event. Each of these black holes likely contains the mass of hundreds of millions of suns, all compressed into a singularity, a point of infinite density. Their gravitational pull is so immense that not even light can escape their grasp once it crosses the event horizon. And now these 2 monsters are circling one another, separated by a distance that, in cosmic terms, is incredibly small, perhaps just a few light years. This isn't a fast, frantic dance. It's a slow, stately, and utterly destructive waltz that unfolds over millions of years. Their mutual gravitational attraction pulls them closer with each passing orbit, a spiral of fate that can only end one way. The energy involved in this orbital decay is almost incomprehensible. As they swing around each other, they literally shake the fabric of spacetime itself, sending out ripples known as gravitational waves. These waves propagate across the universe at the speed of light, a faint echo of this colossal interaction. While we haven't directly detected the waves from this specific pair yet, their existence is a prediction of Einstein's theory of general relativity, and observing a system like this helps us understand how common such cosmic events might be. But the true spectacle isn't just the black holes themselves. it's what they're doing to their surroundings. The gravitational tides from this binary pair are violently reshaping the space around them. Vast clouds of gas and dust pulled from the merging galaxies are being funneled toward the central duo. This material doesn't fall in directly. Instead, it forms immense, whirling structures known as accretion disks, spinning around each black hole at nearly the speed of light. The friction and compression within these disks heat the material to temperatures of millions of degrees, causing it to glow brilliantly across the entire electromagnetic spectrum, from radio waves to visible light and into high-energy X-rays. This process turns the galactic core into an unimaginably powerful engine, a beacon of energy that outshines billions of stars. It's a chaotic, violent, and beautiful factory, forging new elements and hurling jets of particles thousands of light-years into intergalactic space. Yet even as these titans clash at the center, their gravitational struggle is creating spectacular structures far beyond the core, painting the darkness with streams of stolen starlight. As the two galaxies tangle, they don't just push and pull at each other, they tear each other apart. The immense gravitational forces act like a cosmic tidal force, stretching and distilling vast rivers of gas, dust, and stars, flinging them out into the intergalactic void. These are the tidal tails, and in the case of the Mice Galaxies, they are some of the longest and most magnificent ever observed. Enormous, graceful arcs that sweep hundreds of thousands of light-years into space, a permanent scar of this epic collision. But within these seemingly desolate streams of exiled material, something miraculous is happening. These tidal tails are not merely graveyards of old stars, they are vibrant stellar nurseries. The very same gravitational shocks that ripped this material loose also compressed it, triggering frantic bursts of star formation. Imagine a vast, dark nebula suddenly, violently collapsing under its own weight and within a cosmic heartbeat, a mere few million years, igniting into a brilliant cluster of newborn suns. This is the paradox of galactic collisions. They are both agents of destruction and creators of new life. The star clusters forming in these tidal tails, however, are unlike anything we see in the calm spiral arms of a normal galaxy. They are superstar clusters, incredibly massive, densely packed, and perplexingly young. A single one of these clusters can contain the mass of 1 million suns, all crammed into a region of space that would feel claustrophobic to our own solar system. Their density is almost unimaginable. If you were standing on a planet orbiting a star in one of these clusters, your night sky wouldn't be a sprinkling of stars but a continuous, blazing sheet of light. They are the ultimate urban centers of the cosmos, and this presents a profound mystery for astronomers. According to our established models of star formation, such massive, dense clusters should only be able to form in the intense environments near a galactic core, where vast reservoirs of gas and immense pressures are commonplace. Yet here they are, thriving in the deep emptiness of intergalactic space, far from any central gravitational anchor. They are cosmic orphans born from chaos and set adrift. Their very existence forces us to rewrite the textbooks on how stars are born, suggesting that extreme violence might be a more effective midwife than the quiet, steady collapse we once thought was necessary. What becomes of these orphan clusters? Their fate is as uncertain as their origin. Some may eventually be pulled back into the merged galaxy that will one day form from the mice, becoming globular clusters that orbit its halo for billions of years, ancient relics of a violent birth. Others, flung out with even greater force, may truly become intergalactic wanderers, doomed to drift forever in the immense darkness between galaxies, their brilliant light fading over eons into obscurity. They stand as a stunning testament to the fact that even in the most hostile environments, the universe finds a way to create pockets of breathtaking beauty and order. But the chaos isn't confined to the central black holes or the sweeping tidal tails. The incredible gravitational forces at play are capable of launching individual stars into the void with unimaginable speed. Within the turbulent heart of the Mice Galaxies, astronomers have identified one such cosmic projectile, a hypervelocity runaway star, streaking away from the galactic collision like a bullet fired from a celestial cannon. This star's story begins in the most chaotic neighborhood imaginable, the close gravitational grip of the central supermassive black hole binary. Picture a star on a routine orbit, suddenly finding itself caught in the complex, shifting gravity well of two monstrous black holes. As these behemoths swing around each other, their gravity can act like an immense slingshot. In a precise and incredibly rare gravitational interaction, the star is whipped around one of the black holes, gaining a tremendous burst of acceleration before being flung out on a new trajectory, ejected from the galaxy entirely. It's a three-body interaction on a cosmic scale, where the star is the tiny, unpredictable third party that gets thrown clear of the system. The speed this star achieved is what truly boggles the mind. To escape the gravitational pull of an entire galaxy, an object needs to be traveling at a significant fraction of the speed of light. This runaway star is doing just that, blazing through intergalactic space at several million miles per hour. At that velocity, a journey from Earth to the Moon would take mere minutes. Its path is a near straight line, a testament to the sheer force of its ejection, carrying it further into the emptiness between galaxies with every passing moment. By analyzing the light from this stellar fugitive, astronomers can determine its composition, which tells us its life story. This isn't a young, hot blue star born in the recent starbursts. It's likely a middle-aged star, similar to our own Sun or slightly more massive, that was violently uprooted from its original home. Its spectrum provides a chemical fingerprint, revealing it was forged from the same material as the stars in the galactic core, confirming its origin in the thick of the collision. And now, this star is utterly alone. It has left everything it ever knew behind, its sibling stars, any potential planets, the entire galaxy itself. It is now a true intergalactic traveler, destined to spend billions of years crossing the unimaginable voids between galaxy clusters. For any planets that might have been orbiting it, the journey would be a lonely one. The night sky would slowly empty of all other stars until only the faint, blurred glow of distant galaxies remained, receding into ever deeper darkness. This solitary traveler is more than just a curiosity. It's a crucial data point for astrophysicists. Its trajectory is a forensic clue. By tracing its path backwards, scientists can potentially pinpoint the exact location of its ejection, helping to map the precise dynamics of the black hole binary that launched it. Its very existence confirms that these complex gravitational interactions are not just theoretical. They are actively happening, sculpting galaxies and hurling stars into the abyss. Each runaway star is a direct measurement of the incredible forces unleashed during a galactic merger, a natural experiment in extreme gravity that we are fortunate to witness. Now, as we move from the violence of the central black holes and the stellar exiles flung into the void, we encounter perhaps the most profound mystery of all, one that deals not with what we can see, but with what we cannot. Deep within the swirling ballet of the Mice Galaxies, astronomers have mapped the gravitational landscape and found something that shouldn't be there, a massive, invisible anomaly. Through the subtle but powerful technique of gravitational lensing, they have detected a dense, concentrated clump of dark matter lingering in the outer regions of the merging system, a ghostly presence that isn't perfectly aligned with the galaxy's visible stars and gas. Gravitational lensing is like the universe's own scale, allowing us to weigh things we can't see. It works because any object with mass, whether it's a star or a clump of invisible dark matter, warps the fabric of space-time around it. When light from a more distant galaxy travels through this warped region on its way to our telescopes, its path bends much like light bending through a lens. By carefully measuring this distortion in the images of background galaxies, astronomers can create a map of the mass responsible for it, revealing where gravity is strongest. In the case of the mice, this map showed a powerful gravitational tug coming from a place that looked, to all our other instruments, like empty space. This is the telltale signature of a dark matter clump, a hidden concentration of the universe's most elusive substance. The fact that this dark matter isn't perfectly aligned with the visible matter is the key to the entire mystery. During a galactic collision, the various components of a galaxy behave very differently. The clouds of interstellar gas, vast and diffuse, smash into each other head-on. This creates immense pressure, slowing the gas down and causing it to pile up in the central regions, triggering the spectacular bursts of star formation we see. The stars, while countless, are so spread out that they mostly just glide past one another, like two crowds of people passing through each other in a vast square. But dark matter, we believe it doesn't interact with anything, not with light and not with itself. It feels only gravity's pull. So the leading theory predicted that during a merger, the dark matter halos surrounding each galaxy would simply pass right through one another, unaffected by the collision, and continue on their way. The visible gas would lag behind, stuck in the middle. Observations of other colliding galaxy clusters, like the famous Bullet cluster, strongly supported this idea, showing a clear separation between the location of the mass mapped by lensing and the visible matter glowing in X-rays from the hot gas. But here, in the mice, this newly discovered clump complicates that clean picture. It suggests that dark matter might not be completely oblivious to its surroundings. Perhaps there is some faint, unknown interaction occurring within the dark sector itself, a whisper of physics beyond our current models that causes it to clump and lag in ways we didn't anticipate. This single, mysterious object forces us to ask a fundamental question. Does dark matter interact, or does it simply pass through? The answer could reshape our entire understanding of the cosmos. If dark matter has any properties beyond gravity, no matter how subtle, it opens up a whole new realm of particle physics waiting to be discovered. This dense clump, a ghost in the gravitational machine, is more than just an oddity. It is a natural laboratory for testing the very nature of the universe's dominant material. By studying its properties and trajectory, we aren't just looking at the Mice Galaxies, we are peering into the heart of darkness itself, seeking to understand the invisible scaffolding upon which all visible reality is built. Yet as we map the gravitational shadows and luminous wonders of the mice, some of the most compelling mysteries aren't found in what warps the light, but in the light itself. Nestled within one of the galaxy's turbulent spiral arms is an object that glows with an intense, almost feverish heat, but only in a very specific way. This is Object 5, an unidentified infrared object, a point source detected by the Spitzer Space Telescope and now studied in exquisite detail by the James Webb Space Telescope. It emits a staggering, extreme amount of infrared radiation, yet it remains virtually invisible to our optical, ultraviolet, and X-ray telescopes. It's a brilliant heat signature with no obvious face, a cosmic beacon that shouts its presence in a language of pure thermal energy while refusing to show us what it truly is. To understand why this is so strange, think of how most cosmic objects reveal themselves. A star, for instance, is a balanced engine. It shines brightly across many wavelengths, from the ultraviolet light emitted by its scorching surface to the visible light we see and the infrared warmth it radiates. Even a supernova remnant, the chaotic aftermath of a stellar explosion, typically blazes across the spectrum, producing radio waves, visible light, and high-energy X-rays. But this object is different. It is overwhelmingly, almost exclusively, an infrared phenomenon. The amount of energy it pours out as heat is colossal, suggesting a powerful engine is at work. But that engine is completely hidden from our view, shrouded in an incredibly thick, dark cocoon. This deep enshrouding points directly to the first and most plausible explanation: a deeply dust-enshrouded supernova remnant. Imagine a massive star reaching the end of its life and exploding in a cataclysm that would normally outshine an entire galaxy. But instead of that light bursting out into space, the explosion happens right in the heart of an immense, dense molecular cloud, a vast nursery of gas and dust. The initial flash of light from the supernova would be immediately absorbed by this surrounding material, heating it to tremendous temperatures. This superheated dust would then re-radiate all that captured energy as infrared light, creating the exact kind of intense, point-source glow we observe. It would be like witnessing a massive firework exploding inside a thick wool blanket. You wouldn't see the flash, but you'd feel the intense heat radiating from the cloth. In this scenario, we are seeing the echo of a brilliant death, its light transformed into warmth by a cosmic curtain. Another compelling possibility is that we are witnessing the birth of something spectacular, not a death. This could be a nascent globular cluster in its very earliest stage of formation. We know the Mice Galaxies are producing superstar clusters, but perhaps this object is an even rarer and more extreme version. Picture a single, gigantic cloud of gas and dust collapsing under its own gravity with unbelievable ferocity, so dense and turbulent that thousands, perhaps even millions of stars are igniting within it almost simultaneously. But these fledgling stars are still buried deep within their birth cocoon. Their visible light is entirely trapped. Their combined energy, however, heats the surrounding dust to incandescence, creating a brilliant infrared hotspot. We would be looking at the prenatal phase of a future globular cluster, a celestial maternity ward so opaque that we can only detect the warmth of the newborn stars inside. It's a brief, fleeting phase in a cluster's multi-billion-year life, and catching one in the act is an incredible opportunity. Then there is the more exotic, the more speculative possibility, the kind that stretches our understanding of stellar physics to its limit. This object could be a Thorne-Zitkow object, proposed by physicists Kip Thorne and Anna Zitkow. This is a hypothetical stellar hybrid, a red supergiant star so vast it could engulf our entire solar system, but with a mind-bending secret at its core. Instead of the usual fusion engine, a Thorne-Zitkow object harbors a neutron star, the ultra-dense, city-sized corpse of a dead sun orbiting within its own atmosphere, eventually spiraling down to sit at its very heart. The exotic nuclear processes occurring on the surface of the neutron star, buried deep within the envelope of the giant star, would produce unusual elements and an enormous amount of heat. This heat would then diffuse outward, causing the entire enormous star to glow with a distinctive and intense infrared signature, much like what we see in this object. It would be a star within a star, a Russian doll of cosmic proportions, and to date, not a single one has been definitively confirmed to exist. Finding one here, in the chaotic forge of a galactic collision, would be a monumental discovery. The James Webb Space Telescope is now our best tool for solving this mystery. Its powerful infrared eyes are analyzing the precise light signature of this object, looking for subtle chemical fingerprints in the radiation it emits. The specific mix of elements and the exact distribution of its heat could tell us which of these scenarios is correct. Each possibility leaves a different mark. A dust-shrouded supernova would have the spectral traces of specific heavy elements forged in the explosion. A nascent star cluster would show the broad heat signature of countless individual sources. And a Thorne-Zitkow object might reveal the unique isotopic signatures of exotic nucleosynthesis, a type of element formation that can only happen on the surface of a neutron star bathed in a sea of hydrogen. This single, faint point of heat is a perfect example of how modern astronomy works. It's a cosmic detective story where a single clue, an anomaly in the data, opens up a multitude of pathways, each leading to a radically different understanding of the physics at play. Whether it's a hidden death, a secret birth, or a stellar oddity once confined to theory, this unidentified infrared object reminds us that the universe is still full of surprises, waiting for us to look at the familiar sky in a completely different light. Shifting our gaze from the hidden heat of infrared mysteries, we now encounter a structure that is violently, brilliantly apparent, but only if we have the right eyes to see it. In the chaotic expanse between the two colliding galaxies, the Chandra X-ray Observatory has revealed a spectacle of pure energy, a vast, complex formation that astronomers have nicknamed the X-Ray Lobster Nebula. This isn't a cloud of cold gas or a gentle nebula. It is a seething, furious region of space glowing with the most energetic form of light in the universe, a testament to violence on an epic scale. Imagine a colossal lobster carved not from shell but from incandescent multimillion-degree plasma, its claws outstretched as if ready to snap, its body arched and twisted across the darkness. This bizarre and intricate shape, spanning hundreds of light years, is painted in the false colors of a Chandra X-ray image, vivid blues and purples representing the most intense regions of emission. This is the aftermath of a titanic explosion, a shock wave traveling through the interstellar medium at thousands of miles per second, compressing and heating the thin gas between stars until it shines with a fierce, high-energy light. The nebula's complex morphology, with its delicate loops and filamentary structures, tells a story of incredible forces interacting with a turbulent and clumpy environment, creating a shape that is as beautiful as it is destructive. The leading explanation for this high-energy spectacle is a supernova remnant, but not just any remnant. This is likely the expanding debris field from a Type Ia supernova, a specific kind of stellar detonation that occurs in binary star systems. In one scenario, a dense white dwarf star, the Earth-sized cinder of a Sun-like star, siphons material from a companion star until it reaches a critical mass threshold. Instantly, the entire white dwarf undergoes a runaway thermonuclear explosion, unleashing as much energy as our Sun will emit over its entire 10 billion-year lifetime in a single blinding flash. The blast wave from this cataclysm would have ripped through space, slamming into the surrounding gas and dust and creating the intricate shock structures we see today. The X-rays are produced by this superheated plasma and by subatomic electrons, accelerated to nearly the speed of light by the shock front, spiraling around magnetic field lines. However, there is another, equally fascinating possibility, a microquasar. Within our own galaxy, we have observed binary systems where a black hole or neutron star is actively feeding on material from a companion star. As this material falls in, it doesn't go quietly. It can form an accretion disk and launch two powerful, narrow jets of particles traveling at relativistic speeds from its poles. If such a system existed here and one of those jets was pointed nearly in our direction, its intense interaction with the interstellar medium could create a sustained, jet-powered nebula glowing in X-rays. The lobed structure could then be the result of these jets plowing into surrounding gas clouds, much like a fire hose blasting into a pile of sand. But the true heart of the mystery lies at the center of this cosmic crustacean. What power source continues to energize this region? The sheer intensity and persistence of the X-ray emission suggest there is more than just a fading shock wave at work. Many astronomers suspect that lurking within the nebula's core is one of the most exotic and terrifying objects in the universe, a magnetar. A magnetar is a type of neutron star, the ultra-dense collapsed core of a massive star but with a twist. It possesses a magnetic field of almost inconceivable strength, 1,000 trillion times more powerful than Earth's magnetic field. A magnetar's field is so strong it could strip the information from every credit card on Earth from halfway across the galaxy. This unimaginable magnetic energy doesn't just sit there, it actively shapes the environment. A magnetar can experience starquakes, sudden fractures in its rigid neutron star crust that release massive bursts of X-rays and gamma rays. Its rotating magnetic field can act like a colossal dynamo, continually pumping energy into the surrounding supernova remnant, keeping the nebula shining brightly long after the initial explosion should have faded. The flickering, variable nature of the X-ray emission from the lobster core is a key clue that points to a small, spinning, and immensely powerful central engine, making a magnetar the prime suspect. Finding one here in the extreme environment of a galactic collision would provide a unique opportunity to study how these magnetic monsters are born and how they influence their surroundings for millennia after their dramatic formation. Of all the strange sights within the Mice Galaxies, few are as elegantly mind-bending as the phenomenon known as the double Einstein ring. Imagine looking through a vast natural telescope, one that not only magnifies the distant cosmos but also warps its light into a perfect illusion, a series of shimmering, concentric circles hanging in space like a cosmic bullseye. This is precisely what astronomers have observed here, a stunning example of gravitational lensing so precise and rare that it feels almost like the universe is deliberately showing off. The physics behind this marvel is both simple in concept and profound in its implications. It all comes back to gravity's ability to warp the very fabric of space-time, as first predicted by Einstein. In this specific case, the massive foreground galaxy of the mice pair acts as the lens. Its immense gravitational field creates a dimple in space-time, much like a heavy ball placed on a stretched rubber sheet. When light from a much more distant galaxy travels through this warped region on its long journey to Earth, its path is bent. From our perspective, this distortion can magnify the background galaxy's image, stretch it into a faint arc, or, under perfect conditions, smear it into a complete ring of light encircling the foreground lens. This is an Einstein ring, a full 360-degree mirage of a single object. They are rare enough on their own, but here we see something even more extraordinary, two of them. This double ring illusion means we are witnessing a flawless cosmic alignment, a near-perfect lineup of three galaxies across billions of light-years. The foreground galaxy in the mice is bending the light not from one, but from two separate, even more distant background galaxies. Each of these background sources lies at a different distance from us, and the foreground galaxy's gravity bends their light by different amounts, creating two distinct, shimmering rings nestled one inside the other. It's a snapshot of cosmic depth, a glimpse into three different epochs of the universe's history frozen in a single image. This celestial alignment does far more than just create a beautiful picture. It transforms into one of the most powerful natural tools in an astronomer's toolkit. First and foremost, it acts as a natural telescope, magnifying the faint light from those incredibly distant background galaxies. Without this gravitational assist, these galaxies would be far too dim and small for our telescopes to study in any detail. But the lensing effect can brighten their light and Chinese letter their apparent size by a factor of 10 or even 20, allowing us to peer into their structures with unprecedented clarity. We can study the rate of star formation in the infant universe, observe the dynamics of galactic disks when the cosmos was only a fraction of its current age, and test our models of how the very first galaxies assembled themselves. This double ring gives us a free front-row seat to the early universe's most dramatic formative events. Secondly, and just as crucially, this rare double configuration allows for exquisitely precise cosmic cartography. By carefully measuring the exact geometry and thickness of each ring, astronomers can perform a rigorous gravitational audit of the lensing galaxy itself. The subtle distortions within the rings act as a direct map of how mass, both visible stars and invisible dark matter, is distributed throughout the foreground galaxy. It's like taking an X-ray of the galaxy's gravitational skeleton. The presence of the second ring is especially valuable because it provides a second, independent measurement, cross-checking the results from the first and yielding a far more accurate and reliable model of the galaxy's total mass and its distribution. This helps us understand the properties of dark matter on a galactic scale with a precision that would be impossible through any other means. The double Einstein ring in the Mice Galaxies is therefore more than a curiosity. It is a perfect natural laboratory. It is a phenomenon that simultaneously allows us to gaze out into the deepest reaches of time and space while also turning our focus inward to precisely weigh and measure the hidden components of the galaxy right before us. It is a single observation that unlocks secrets across cosmic epochs, a true testament to the fact that sometimes the universe's greatest wonders are not the objects themselves, but the beautiful, twisted paths their light takes to reach us. While we've marveled at stars being flung into the void and immense structures carved by gravity, the chaos of the Mice Galaxies likely produces exiles on a far smaller, yet equally profound scale. Imagine not a star but a world, a planet perhaps once cradled in the habitable zone of a stable star with oceans and continents and skies. Now imagine that world violently torn from its solar system by a gravitational shockwave during the galactic collision, set adrift into the freezing, lightless space between the stars. This isn't science fiction, it's a probable reality. Astronomers suspect the mice are generating a population of rogue planetary mass objects, lonely, frozen worlds on perpetual journeys through the abyss. The mechanism of their ejection is a testament to the sheer disruptive power of a galactic merger. In a stable system like our own, planets follow predictable orbits around their sun, held in a delicate balance by gravity. But when two galaxies collide, that gravitational harmony is shattered. A star minding its own business can have a close encounter with another star passing through, their mutual gravity slingshotting each other into new trajectories. For any planets orbiting those stars, the result is catastrophic. The sudden, violent jerk on their host star can easily break their gravitational tether, flinging them out of the system entirely at incredible speeds. Alternatively, a planet could be stolen by the passing star, only to be discarded later during another gravitational interaction. It's a cosmic game of pinball, and the planets are the balls battered around until they're lost to the darkness. The fate of these rogue worlds is a haunting one. Ejected from the warmth of their sun, their surfaces would rapidly cool to temperatures only a few degrees above absolute zero. Any atmospheres would freeze solid, collapsing into icy deposits on the ground. Any potential oceans would become global, kilometers-thick ice sheets. Devoid of an internal heat source like the radioactive decay that powers geological activity inside Earth, these worlds would become geologically dead, frozen statues preserving a moment of their past for eternity. They would drift in utter blackness, their nights permanent, their only source of light the faint collective glow of the galaxy they were expelled from, receding slowly into the distance over millions of years. Detecting such a dark, cold, and isolated object is one of the greatest technical challenges in modern astronomy. They emit no light of their own and reflect far too little starlight to be seen by conventional telescopes. The key to finding them lies not in seeing their light, but in observing how they bend the light of others through a phenomenon called gravitational microlensing. Here's how it works according to Einstein's theory. Any object with mass warps the fabric of spacetime. When one of these rogue planets drifts almost perfectly in front of a much more distant background star, its gravity acts as a tiny lens, focusing and briefly amplifying the light from that star. From our perspective, the background star will appear to temporarily brighten in a very specific, predictable way, a sharp rise to a peak, followed by a symmetrical decline. The duration and shape of this light curve tell us the mass of the object causing the lensing. For a planet-sized object, this brightening might only last for a few hours or days. Future observatories like the Nancy Grace Roman Space Telescope are specifically designed to conduct vast microlensing surveys, monitoring hundreds of millions of stars in the galactic bulge continuously, just waiting for these telltale flashes. The chaotic, star-rich environment of the Mice Galaxies makes it a prime hunting ground for such events. Every single microlensing detection is a data point, helping us build a statistical census of this hidden population of lonely worlds. It's a form of cosmic archaeology, using these faint signals to uncover the history of violence that created them. The existence of these rogue planets tells a profound story about the fragility of cosmic order. We often think of planetary systems as stable, permanent homes, but the Mice Galaxies show us that on galactic timescales they can be terrifyingly transient. A merger can act like a great reset button, scattering countless worlds into the void and potentially sterilizing entire regions of a galaxy of any life that may have taken root. It forces us to ask a deeply philosophical question. In a universe where such chaos is common, is life elsewhere inevitably a fleeting phenomenon, constantly being snuffed out by galactic events before it can become interstellar? Or could life, in some incredibly resilient form, even persist on one of these frozen rogue worlds, buried deep in a subsurface ocean kept liquid by gravitational tidal heating or radioactive decay, completely isolated from any star, adrift in the eternal night? The possibility, however slim, transforms these lonely exiles from mere cosmic debris into some of the most mysterious and intriguing objects in the entire galaxy. Moving from the silent journeys of rogue planets, we now turn our attention to a structure that, while invisible to our eyes, shouts its presence across the radio spectrum. Suspended within the turbulent aftermath of the galactic collision is a vast ethereal loop, a celestial smoke ring on a scale that defies easy comprehension. Discovered by the most sensitive radio telescopes, this anomalous radio loop is a giant, faint structure that emits synchrotron radiation, a specific type of radio wave generated by electrons spiraling at nearly the speed of light around magnetic field lines. Its ghostly form is unmistakable, a perfect arc hanging in space. Yet, when astronomers point their optical and X-ray telescopes at the exact same coordinates, they find nothing. A profound emptiness, this disconnect between what we hear in radio and what we see in other wavelengths, makes this loop one of the most puzzling structures in the entire system, a ghost in the machine begging for an explanation. The most immediate and compelling theory points to the aftermath of a stellar cataclysm. This loop could be the fossil remnant of a supernova that exploded not centuries but millions of years ago. In the vibrant aftermath of a supernova, the expanding shock wave acts as a colossal particle accelerator, boosting electrons to relativistic speeds and amplifying magnetic fields. These high-energy electrons then spiral along the magnetic field lines trapped within the expanding shell, producing the synchrotron radio glow that defines a classic supernova remnant. Over time, however, the remnant expands and dissipates. The hot gas that once glowed in X-rays cools and becomes too diffused to detect. The ejected material that was initially visible spreads out and fades into the background. But the electrons and the magnetic field they travel through can persist for far longer, continuing to emit their faint radio whisper long after every other sign of the explosion has vanished. This radio loop could therefore be the ghost of a supernova, a fading echo of a stellar death that occurred eons ago, its visible body gone but its energetic soul still lingering in the void. But the sheer size of this structure gives some astronomers pause. Could a single supernova create a remnant this immense? This question opens the door to a more powerful and exotic possibility, a relic jet from an active galactic nucleus. We know the Mice Galaxies host a supermassive black hole binary at their core, a dynamic engine capable of launching jets of plasma at relativistic speeds. These jets can extend for hundreds of thousands of light years, and when they eventually stall and lose their energy, they don't just disappear. The particles within them can drift away, spreading out but still tracing the path of the original jet's magnetic skeleton. What we might be seeing is the decaying, off-axis lobe of a jet that was once fired by one of the central black holes, perhaps during an earlier, more active phase of the merger. This relic would be a fossil of past galactic violence, a testament to a time when the core of the mice was an even more powerful and furious engine than it is today. Its radio glow would be the fading signature of that immense directed power. There is a third, equally fascinating hypothesis that looks not inward to the galaxy's core, but outward to its past interactions. This perfect loop could be the final, dissolving signature of a dwarf galaxy that was cannibalized by the mice long before the current major collision began. In this scenario, as the small galaxy was drawn in and torn apart by tidal forces, its gas would have been stripped away and compressed. This compression could have triggered a final, frantic burst of star formation within the doomed galaxy's own gas, creating a wave of massive stars that lived fast, died young, and exploded as supernova in quick succession. This chain reaction of explosions, all occurring within the same confined stream of tidally stripped gas, could have created a single, coherent, bubble-like structure, a supernova superbubble that we now observe as this coherent radio loop. It would be the last collective gasp of an entire galaxy, a final star-forming breath before it was completely consumed and digested by its larger neighbor. The key to solving this mystery lies in the subtle details of the radio emissions themselves. By analyzing the polarization of the radio waves, astronomers can map the magnetic field lines within the loop. A tangled, turbulent field might point toward a supernova remnant where the explosion creates chaos. An ordered, linear magnetic field structure, however, would strongly support the relic jet hypothesis, as jets often impart a high degree of order to the magnetic fields within their lobes. Furthermore, deep, ultra-sensitive observations hunting for any faint, corresponding optical light or even the faintest X-ray glow could provide the crucial smoking gun. The detection of even a whisper of optical filaments would confirm the presence of shock-heated gas, nailing the supernova remnant theory. The complete and utter absence of any other wavelength signature, making it a pure radio phantom, might make the relic jet or the dwarf galaxy remnant the most compelling answer. This enigmatic loop is a reminder that the universe leaves behind many different kinds of fossils, not just of stars and planets, but of magnetic fields, particle beams, and entire galactic digestion events, each telling a story of past violence written in a language of light we are only just learning to read. Drifting through the gravitational turmoil of the merging mice, like a venerable old ship caught in a storm between two mighty fleets, is a celestial relic that simply doesn't belong. This is an ancient globular cluster, a dense sphere of nearly 1 million stars bound together by gravity, and it is behaving very strangely. Its orbit around the nascent merged galaxy is chaotic and wildly unstable, a clear sign that it is not a native to this new system. Astronomers believe this entire cluster was stolen, gravitationally plundered from one of the original spiral galaxies during the first close passes of the collision. It's a cosmic prize of war now caught in the gravitational crossfire, and its future is entirely uncertain. The true story of this cluster's origin, however, is written not in its motion but in its light. By analyzing its spectrum, astronomers can perform a kind of chemical archaeology, determining its metallicity, a term that in astronomy refers to the abundance of elements heavier than hydrogen and helium. These heavier elements, like iron, silicon, and oxygen, are forged in the nuclear furnaces of massive stars and are then scattered across space when those stars die in supernova explosions. Subsequent generations of stars form from this enriched gas, each one born with a higher metallicity than the last. This means a star's metallicity acts as a timestamp. The older the star, the lower its metal content, because it formed before many supernova had a chance to seed its environment. This precariously balanced cluster has an exceptionally low metallicity. Its stars are pristine, ancient, and metal-poor. This single measurement tells us that this globular cluster is one of the very first structures to have formed in the entire universe, likely coalescing from the primordial gas that existed just 1 billion or 2 years after the Big Bang. It is a fossil from the universe's childhood, a time before the cosmos had been widely seeded with the heavy elements that make up planets and ultimately life. Its presence here is a profound clue. It likely originated in the halo of one of the original Mice Galaxies, a relic from that galaxy's own violent formation over 10 billion years ago. It has been orbiting its parent galaxy since the beginning, a faithful retainer for eons, until a collision violently broke that bond. Now, this ancient wanderer finds itself in a gravitational dilemma. It is no longer orbiting a single, stable galaxy. It is navigating the complex and shifting gravity well of a messy merger, a system dominated by a central black hole binary and a dark matter halo that is still settling. Its current path is a wobbly, unpredictable roller coaster. Computer simulations of its trajectory show a disturbing number of potential outcomes, and many of them don't end well. It could be slingshotted inward, destined to be torn apart by the terrifying tidal forces near the galactic center, its stars scattered and assimilated into the larger population. Or, in a fitting twist of fate for such an ancient traveler, it could be flung outward entirely. This second possibility is perhaps the most fascinating. The same gravitational interactions that stole it from its original home could now grant it a form of cosmic freedom. A precise gravitational kick from the central black hole binary could eject it from the galaxy altogether, boosting its velocity beyond the system's escape speed. It would then become what is known as an intracluster globular cluster, a lone globular cluster that belongs not to any single galaxy, but to the vast gravitational field of the entire galaxy group or cluster that the mice reside within. It would leave the scene of the collision behind, sailing off into the incredible emptiness of intergalactic space. Its journey from that point would be one of profound isolation. For billions of years, it would travel through the darkness, its million suns providing the only source of light in an endless night. The view from any planet within that cluster would be breathtakingly lonely. The night sky would be dominated by the dazzling, dense cloud of nearby stars, while the merged galaxy of its birth would slowly shrink into a faint, fuzzy patch of light before eventually disappearing from view entirely. It would become a permanent wanderer, a self-contained island universe adrift in the cosmic ocean. The potential ejection of such a cluster is more than just a curious astronomical event. It has significant implications for our understanding of how the universe is structured. If intracluster globular clusters are common, they could contribute a substantial amount of mass to the invisible halos of galaxy clusters. They could even act as tracers, helping us map the intricate and otherwise invisible gravitational web of dark matter that binds the entire cosmos together. This one precarious cluster, therefore, is a key to understanding not only its own dramatic past, but also the distribution of matter on the very largest scales. Its unstable dance is a momentary snapshot in a billion-year journey, a testament to the fact that even the oldest objects in the universe can still have their futures completely rewritten by cosmic violence. Amidst the sprawling stellar nurseries and the echoing remnants of past explosions, the Mice Galaxies hold a stellar time bomb, a star so massive and unstable that its very existence seems like a defiance of physics. This is a luminous blue variable, one of the rarest and most massive types of stars in the universe, and it is currently in a phase of its life that can only be described as a prolonged, violent tantrum. Located within one of the brilliant superstar clusters forged by the galactic collision, this star is a behemoth, likely born with well over 100 times the mass of our own Sun. Its incredible bulk generates a ferocious internal furnace, burning through its nuclear fuel at a reckless rate that gives it a lifetime measured in mere millions of years, a fleeting blink compared to our Sun's 10 billion-year lifespan. The defining characteristic of a star like this is its profound instability. It doesn't shine with a steady, constant light like most stars. Instead, it experiences wild, unpredictable swings in brightness. For years or even decades, it might blaze with a serene, blue-white intensity. Then, without warning, it can enter a violent eruptive phase. the star's own radiation pressure becomes so immense that it overwhelms the gravity struggling to hold the star together. This causes the star to literally puff up, ejecting enormous shells of its own outer atmosphere into space in a series of colossal eruptions. During these events, the star can temporarily swell to a much larger size and its luminosity can skyrocket, making it one of the brightest objects in the entire local region of the galaxy. After the eruption subsides, the star contracts again, returning to its hotter, bluer state, only to begin building toward the next inevitable outburst. It's a star living on the edge, constantly battling between the outward push of radiation and the inward pull of gravity. The material ejected during these eruptions doesn't just disappear. It accumulates around the star, forming a complex, expanding nebula of its own creation. In many ways, this star is sculpting its own tomb. These ejected shells are rich in heavy elements that were forged in the star's core: carbon, nitrogen, oxygen, and they are being recycled back into the interstellar medium, providing the raw materials for future generations of stars and planets. We are essentially watching a key part of the cosmic life cycle play out in real time, as a massive star seeds its environment with the very elements that are essential for life. The nebula around this particular variable star, illuminated by the star's intense ultraviolet light, is a beautiful and intricate structure, a gossamer envelope of glowing gas that tells the history of its creator's violent mood swings. But the most thrilling and ominous aspect of this star is its future. Luminous blue variables are widely believed to be the direct progenitors of some of the most powerful explosions in the universe, type I supernova and perhaps even long-duration gamma-ray bursts. Because these stars have already shed so much of their outer hydrogen envelopes through their constant eruptions, when they finally do reach the end of their lives and their cores collapse, the resulting supernova explosion slams into all that previously ejected material. This creates a spectacular and long-lasting light show, a supernova that can remain bright for months or even years as the shockwave plows through the circumstellar debris. For a star of this mass, the core collapse could happen at literally any moment. There is no way for us to predict it. It could happen in 10,000 years, or it could happen 10 minutes from now. The light from that cataclysm is already on its way to us. We just don't know when it will arrive. This makes observing this star an incredibly urgent and exciting endeavor for astronomers. Every new observation could be the one that catches the first signs of its final death throes. Powerful telescopes monitor its brightness and spectrum regularly, looking for any telltale changes that might hint at an impending collapse. A supernova from this star would be a landmark event, temporarily outshining its entire host galaxy and providing an unprecedented opportunity to study the final moments of a truly monstrous star in exquisite detail. It would be a cosmic spectacle visible across millions of light years, a fittingly dramatic end for a star born from one of the most dramatic events in the universe, a galactic collision. Until that moment comes, it remains a brilliant, unstable sentinel, a reminder of the beautiful violence that defines the life and death of the universe's most massive stars. Stretching between the two colliding galaxies and reaching far out into the surrounding darkness is a structure so vast it defies earthly comparison, a river of primordial gas on a cosmic scale. This is the intergalactic HI bridge, a tenuous but enormous filament of neutral hydrogen atoms weaving through the void. While our eyes and optical telescopes see only black emptiness between the galactic mice and their long tidal tails, radio telescopes tell a completely different story. They reveal a faint but definitive signature, the 21-centimeter line emission, painting a picture of this incredible bridge that serves as both a fossil of the collision and a promise of things to come. The genesis of this structure lies in the very first gravitational passes of the two galaxies. As they swung by each other, their mutual gravity didn't just pull on the stars, it acted most strongly on the immense reservoirs of cold, neutral hydrogen gas that filled their disks. This gas, diffuse and responsive, was much more easily pulled and stretched than the stars were. Think of it like two wet paintbrushes swinging past each other. The stars are like the bristles, mostly staying put, but the gas is like the droplets of paint flung out into long, connecting strands between them. This bridge is the literal connective tissue of the collision, a gravitational filament spun from the very raw material of the galaxies themselves. What's truly remarkable about this hydrogen is its pristine nature. This isn't gas that has been cycled through multiple generations of stars, enriched with heavy elements, and then blown back out by supernova. Spectroscopic analysis shows it is overwhelmingly composed of primordial hydrogen and helium, the basic building blocks of the universe forged in the Big Bang. This means we are looking at gas that has been relatively undisturbed for billions of years until now. The collision has dredged up material from the outer, untouched regions of the galactic disks and flung it out into intergalactic space, giving us a rare chance to study matter almost exactly as it was before stars ever got to work on it. It's a cosmic time capsule offering a direct window into the early conditions of galaxy formation. But this bridge is far more than a static relic. It is a reservoir of potential. All that neutral hydrogen is the primary fuel for star formation. Right now, the gas in the bridge is too diffuse and too turbulent to collapse under its own gravity. It's like a cloud bank spread thinly across an entire continent. However, the future holds incredible promise. Over the next hundreds of millions of years, as the merged galaxy settles into a new, stable form, likely an elliptical galaxy, this bridge will not simply dissipate. Its own gravity will begin to pull it together. Clumps will start to form within the filament, regions of slightly higher density that will act as seeds. These clumps will slowly, inexorably, draw in more and more gas from the surrounding filament. As they grow denser, they will eventually cross a threshold and begin to collapse, igniting into brilliant new stars. We could be witnessing the very early, slow-motion birth of an entirely new population of stars, but with a twist. These stars will not be born within a galaxy. They will form in the isolated darkness of intergalactic space, far from the bright lights of the merged Mice Galaxy. They will become the first generations of stars in a new dwarf galaxy, or perhaps a series of star clusters that will orbit the main galaxy like distant moons. This bridge is not just a consequence of destruction, it is the blueprint for a new creation, a stellar nursery in the making on a timescale almost too long to comprehend. For astronomers, this structure is an invaluable tracer, a living map of the collision's history and mechanics. The precise distribution, density, and velocity of the gas within the bridge tells a detailed story. By measuring how the gas is moving, scientists can work backwards to model the exact angles and speeds of the galaxy's initial encounters. Subtle kinks or variations in the bridge's structure can indicate the influence of dark matter subhalos or the gravitational tug of smaller, unseen satellite galaxies. It acts as a forensic record, its currents and flows encoding the secrets of the gravitational forces that shaped it. In many ways, this faint radio whisper is one of the most eloquent narrators of the entire cosmic event, telling a story of past violence and future promise written in the simplest atom in the universe. Among the slow, majestic violence of a galactic merger, some events unfold in a blinding instant. This brings us to our 13th strange object, a phenomenon that wasn't an object at all, but a singular, catastrophic event. A brilliant, fleeting flash of the highest energy light in the universe. Without warning, space-based gamma-ray observatories registered an immense spike of energy originating from the direction of the Mice Galaxies. This was a gamma-ray burst, one of the universe's most powerful explosions, a flare so intense that for a few seconds it likely outshone every other star in both colliding galaxies combined. But as quickly as it appeared, it was gone, leaving behind only a fading afterglow and a monumental forensic challenge for astronomers. pinpointing the exact source of such a transient event within a chaotic 300 million light-year distant collision is a feat of modern cosmic detective work. The initial gamma-ray detectors provided a rough location, an error box that could have contained millions of stars. The real work began in the minutes and hours that followed, as automated systems swung ground-based and space-based telescopes into action, frantically searching for the afterglow. A gamma-ray burst doesn't just vanish, it leaves a fading fingerprint across the spectrum, from X-rays down to radio waves. It was this fading light that astronomers hunted, and when they found it, they were able to trace it back to a very specific location within one of the Mice's turbulent spiral arms, a region already scarred by recent starburst activity. So what could have caused such a titanic detonation in this already violent neighborhood? The evidence points toward two primary suspects, each with dramatic implications. The first is the death of a very specific kind of star. This could have been the final collapse of a rapidly spinning, extremely massive star, a type of event known as a collapsar. In this scenario, the star's core catastrophically collapses into a black hole. As it does, it launches ultra-relativistic jets of plasma from its poles, punching straight through the star's outer layers. If one of those jets is pointed directly at Earth, we see it as an incredibly bright gamma-ray burst. The fact that the mice are actively forming massive, short-lived stars makes this a strong possibility. It's an environment ripe for such spectacular deaths. The second, and perhaps even more exotic possibility, is the merger of two ultra-dense stellar corpses. Imagine a binary system where two neutron stars, or a neutron star and a black hole, have been locked in a slow, decaying orbit for millions of years. As they spiral closer, they radiate energy away in gravitational waves until finally they collide. The resulting cataclysm is a multi-messenger event of unbelievable violence. It forged elements heavier than iron, like gold and platinum, in its wake, and for a brief moment, it can also produce a short gamma-ray burst as a jet of material is launched from the merger debris. The dense stellar environment of the mice would be a perfect breeding ground for such binary systems to form and eventually meet their end. The aftermath of such an event is just as fascinating as the explosion itself. In the days and weeks that followed the initial flash, astronomers watched the location carefully. The fading afterglow caused by the expanding shockwave from the burst plowing into the surrounding interstellar medium provided crucial data on the energy released and the density of the local environment. Furthermore, if this was indeed a neutron-star merger, the site should now be enriched with a vast cloud of newly synthesized heavy elements, a literal cloud of gold and other precious metals forged in the heart of the collision. While this material would be dispersed and impossible to see directly at this distance, its theoretical presence completes the picture of a truly universe-altering event. This single, brief flash of light serves as a powerful reminder that the Mice Galaxies are not just a static scene of slow-motion collision. They are a dynamic ecosystem where transient, high-energy events regularly occur. Each gamma-ray burst is a punctuation mark in the life of a galaxy, a sudden, violent end that seeds the future with the elements for new stars, new planets, and perhaps one day new life. It shows us that even after hundreds of millions of years, the story of this collision is still being written in bursts of incredible energy, visible across the cosmos. Nestled within the fiery chaos of a superstar cluster, a region where massive stars are being born and dying in rapid succession, astronomers have found something that logic insists should not exist: a delicate, swirling disk of gas and dust, pristine and intact, encircling a very young star. This is a protoplanetary disk, the very cradle of planet formation, and its presence here, in one of the most violent neighborhoods in the universe, is nothing short of miraculous. It's a cosmic David surviving amidst 100 Goliaths, a tiny, ordered system persisting in a maelstrom of destructive forces. To understand why this disk's survival is so baffling, consider the threats it faces. The intense ultraviolet radiation pouring from nearby massive stars is so powerful it has the ability to literally boil away the gas in a disk like this, a process called photoevaporation. It can strip a fledgling solar system of its raw materials in a relatively short amount of time, halting planet formation before it can even properly begin. On top of that, the gravitational tides from passing stars and the overarching pull of the merging galaxies themselves should be enough to tear the disk apart, shredding its delicate structure or flinging it entirely away from its host star. The environment is akin to trying to carefully assemble a house of cards in the middle of a hurricane. Yet, against all odds, this disk endures. Its continued existence suggests it formed very recently, perhaps in a small, unusually dense pocket of gas that collapsed quickly, giving it less time to be disrupted before its star ignited. The star itself may also play a role. If it is particularly active, its own magnetic fields and stellar winds could be creating a protective buffer, a small cocoon that helps deflect the worst of the external radiation and particle flows. It's also possible the disk is simply incredibly massive, so thick and dense that the destructive external forces are only slowly eroding its outer layers, leaving a rich reservoir of material in the inner regions untouched and ready to coalesce into planets. The implications of this resilient disk are profound. It boldly suggests that planet formation is not a process reserved for the quiet, peaceful suburbs of stable galaxies. It can, and apparently does, occur everywhere, even in the most extreme and hostile environments the universe has to offer. If planets can form here amidst the chaos of a galactic collision, then they could be forming in the hearts of active starburst galaxies, around stars in globular clusters, or even in the tidal tails flung far into intergalactic space. The potential for planets, and therefore the potential for life, may be far more widespread and tenacious than we ever imagined. This isn't just a theoretical possibility, we can already see the process at work. Observations from the Atacama Large Millimeter Array have captured stunningly detailed images of this very disk, revealing distinct gaps and rings within its structure. These are the classic hallmarks of planet formation, the telltale signs that dust and rocks are already clumping together, clearing out their orbits as they slowly grow into full-fledged protoplanets. We are witnessing the birth of a solar system in real time, and it's happening in the last place we would ever think to look. This tiny, defiant disk is a powerful testament to the universe's relentless drive to create order from chaos, to build new worlds no matter the odds. Yet as we marvel at the resilience of a single planet-forming disk, we are reminded that the vast majority of matter in the universe plays by a completely different set of rules, a truth that leads us to one of the most profound enigmas in the entire Mice system. Tucked away in the galactic outskirts, far from the brilliant starbursts and tidal streams, lurks a gravitational phantom. Through meticulous mapping of the motions of stars and the subtle warping of background light, astronomers have pinpointed a massive concentration of matter, a region of space where gravity's pull is unmistakably powerful. Yet when they turn every available telescope toward this spot, searching for the source of this pull, they find a profound and puzzling absence. There is no glittering spiral, no faint dwarf galaxy, not even a sparse cluster of old stars. There is simply nothing, or at least nothing that emits any light we can detect. This is a dark galaxy candidate, a vast island of invisible mass that appears to have failed at the most fundamental task of a galaxy, making stars. The evidence for this object's existence is compelling, built on two independent pillars of astronomical detective work. The first is dynamics, the study of motion. By observing the velocities of visible stars and gas clouds that trace the outer edges of this gravitational anomaly, astronomers can measure how fast they are moving. Just as the planets in our solar system orbit faster the closer they are to the Sun's strong gravity, These tracer objects are moving at speeds that can only be explained if they are orbiting an immense unseen mass. The math is clear and inescapable. There is far more gravity here than the visible matter can account for. The second line of evidence comes from the phenomenon of weak gravitational lensing. The immense mass of this candidate warps the fabric of spacetime around it, minutely distorting the shapes of thousands of background galaxies that lie far beyond it. By statistically analyzing this subtle distortion, scientists can create a detailed map of the mass responsible for it, and once again, the map reveals a heavy, compact clump with no luminous counterpart. It is a ghost revealed only by the way it pushes and pulls on the things around it. So what exactly is this thing? One possibility is that we are witnessing a true dark galaxy, a halo of dark matter that, for some reason, never managed to attract and retain enough baryonic or normal matter to spark significant star formation. In the early universe, dark matter halos are thought to have acted as gravitational seeds, drawing in vast clouds of primordial gas that eventually cooled, condensed, and fragmented into the first stars. But in this case, something may have gone wrong. Perhaps this particular halo formed in a region of the cosmic web that was unusually devoid of gas, a desert where there simply wasn't enough raw material to build with. Alternatively, any gas it did acquire early on might have been violently stripped away by a close encounter with another galaxy long before the current Mice collision began, or heated to such extreme temperatures by a nearby burst of radiation that it was prevented from ever cooling down and collapsing. The result is a galactic-scale object that remains, for all intents and purposes, a bare skeleton of pure dark matter. Another, more interactive theory suggests this might not be an independent object at all, but rather the stubborn, surviving core of a small dwarf galaxy that is currently in the process of being cannibalized by the larger Mice system. In this scenario, the dwarf galaxy did once have stars, but as it was drawn into the gravitational pull of the Mice and began its death spiral, the relentless tidal forces stripped away its stars and gas, scattering them into faint, undetectable streams. What remains could be the dwarf's dense, dark matter heart, which is far more resistant to tidal disruption. This resilient nugget of dark mass would now be orbiting within the Mice, a nearly invisible reminder of a past act of galactic consumption. Its presence would help explain how large galaxies grow, not just by colliding with equals, but by devouring countless smaller satellites, digesting their stars and gas, but often leaving their dark matter cores intact. The existence of such an object, regardless of its origin story, presents a monumental challenge to our models of galaxy formation. It forces us to confront a very basic question: is it possible for a dark matter halo to completely fail at forming stars? And if so, how common are these dark failures compared to the shining successes we see everywhere? Finding and studying more of these dark galaxy candidates is crucial, as they could represent a missing piece in our understanding of the cosmic hierarchy. They might be the invisible building blocks that theories like lambda cold dark matter predict, the countless small halos that should exist but have, until now, remained hidden from our view. This ghost in the Mice Galaxies is more than a curiosity. It is a direct probe into the most dominant yet most elusive component of our universe, a silent reminder that most of the cosmos is built from something we cannot see, and that sometimes the most massive structures are the ones that leave no light for us to follow. Amidst the grand tapestry of galactic collision, some of the most fascinating dramas unfold on a far more intimate scale, between two stars locked in a perilous gravitational embrace. Our next object is one such pair, a stellar oddity known as a symbiotic star system. This isn't a typical binary, it's a cosmic partnership that borders on parasitism, a relationship between two vastly different stars that creates a cycle of slow buildup and violent release. The system consists of a bloated, aging red giant and the incredibly dense, Earth-sized corpse of a sun-like star known as a white dwarf. They orbit one another at a distance that feels claustrophobic by stellar standards, and this proximity creates a dynamic that is both beautiful and destructive. The red giant is the donor in this unequal partnership. Having exhausted the hydrogen fuel in its core, it has swelled to a colossal size, its outer atmosphere becoming a tenuous, extended envelope that is only loosely bound by gravity. This star is essentially bleeding its own material into space, creating a persistent and powerful stellar wind. The white dwarf, its companion, is the recipient. Though small, its density is astronomical, packing roughly the mass of our Sun into a volume no larger than Earth. This gives it an immensely powerful gravitational field for its size. As the two stars swing around their common center of mass, the white dwarf plows through the red giant's extended atmosphere, its gravity greedily capturing a fraction of that outflowing wind. This stolen gas doesn't just fall onto the white dwarf's surface quietly. It is funneled into an incredibly hot and bright accretion disk that spirals around the dense corpse star, a whirlpool of superheated plasma that shines with intense ultraviolet radiation. For long periods, this system might appear relatively stable from the outside, a faint point of light with unusual colors, but this stability is an illusion. The white dwarf's surface is a place of extreme conditions, immense gravity and scorching temperatures. The hydrogen-rich gas siphoned from the red giant piles up on the white dwarf's surface, compressed under layers of new material. Over decades or even centuries, the pressure and temperature at the base of this accreted layer steadily increase. Eventually, they cross a critical nuclear threshold. The hydrogen ignites in a runaway thermonuclear fusion reaction, not deep in the star's core, but right there on its surface. The entire accumulated layer of fuel detonates in a colossal blast. From our distant vantage point, we witness this event as a nova. The system's brightness can increase by tens of thousands of times in a matter of days, suddenly making it one of the most prominent stars in its local region of the Mice Galaxies. This isn't a supernova. The white dwarf itself survives the explosion. It simply blows the excess material it had stolen back out into space in an expanding shell of hot, enriched gas, and then the cycle begins anew. It's a stellar heartbeat, a slow fill followed by a sudden, violent purge, repeating over and over again. The existence of such a system in the Mice Galaxies is particularly intriguing because its very formation might be a direct product of the galactic collision. In a quiet, isolated galaxy, the orbits of binary stars are generally stable over billions of years. But the gravitational shock waves and close stellar encounters that ripple through the mice during the merger could have drastically altered the fate of many such pairs. A previously wide, stable binary system could have been perturbed, its orbit tightened through a series of gravitational interactions with passing stars. This could have thrown the two stars into the dangerously close dance we see today, initiating the symbiotic relationship. Alternatively, the collision could have actually forged the pair, bringing two single stars together in a new gravitational bond amidst the chaos. The enhanced density of stars in the merger's core increases the probability of such dramatic encounters, making the mice a perfect breeding ground for stellar oddities that would be exceedingly rare elsewhere. This system is a microcosm of the larger collision, a relationship defined by theft, tension, and violent outbursts, all playing out on a scale that reminds us the grandest cosmic events can create the most peculiar, intimate partnerships. Now, as we look beyond the intimate dances of binary stars and the ghostly presence of dark matter, we set our sights on a structure that seems to defy the very plane of reality itself. Orbiting the main body of the merging mice, there is a peculiar swirl of debris that doesn't follow the rules. While most of the gas, dust, and stars are settling into a flattened disk around the new galactic center, this material is moving in a completely different direction, tracing a wide, looping path that is almost perpendicular to everything else. This isn't just random chaos, it's the potential birth of one of the rarest and most telling structures in the universe, a polar ring. Imagine a Saturn-like ring, but on a galactic scale, encircling the main galaxy not along its equator but around its poles. It's a cosmic hula hoop spun at a dizzying angle, and its existence would tell a dramatic story of how this galaxy has grown over billions of years. The formation of such a ring is a cosmic accident of the highest order, and it almost always points to a specific type of galactic cannibalism. The leading theory is that this ring is the final, dissolving remnant of a smaller satellite galaxy that was captured and torn apart by the mice long ago. Picture a small, gas-rich dwarf galaxy, perhaps one that had been orbiting the larger spiral for eons. During the initial gravitational tugs of the current collision, its orbit was destabilized. Instead of a dramatic head-on collision, it was drawn into a very specific polar orbit, a path that took it sweeping over the galactic poles. As it made these repeated passes, the immense tidal forces of the main galaxy acted like a gravitational cheese grater, slowly but surely shredding the smaller galaxy apart. Its stars were scattered, but its vast reservoir of cold gas and dust was stretched out into a long, streaming arc that eventually settled into this stable, perpendicular orbit. We are not seeing a structure that formed from within. We are seeing the ghost of a meal, the galactic equivalent of a fossilized bone from something the mice consumed. This captured debris is more than just a celestial memorial. It's a powerful forensic tool. The material in this ring retains a memory of its original orbit and composition. By studying the motion of the gas and stars within it, astronomers can effectively rewind the tape, tracing its path backwards to understand the precise trajectory of the dwarf galaxy that was consumed. This allows them to reconstruct a merger event that may have occurred a billion years ago, an act of galactic accretion that would otherwise be completely invisible to us. Furthermore, because this ring orbits over the poles, it gives us a unique, three-dimensional view of the main galaxy's dark matter halo. The speed of the ring's rotation is governed by the gravitational pull of all the mass inside its orbit, which is predominantly dark matter. By mapping the ring's velocity, we can precisely weigh and measure the shape of the invisible dark matter sphere encasing the galaxy, providing some of the most compelling evidence for its existence and distribution. The presence of a forming polar ring also tells a story of resilience and creation amidst destruction. Within this swirling river of captured gas, the conditions can be ripe for a new wave of star birth. The gas, compressed by the very forces that captured it, can collapse to form new stars. This means the ring can become a band of young, blue stars, a brilliant, sparkling hoop of new life that stands in stark contrast to the older, yellower stars of the main galaxy below. It creates a galaxy with two distinct populations of stars moving in perpendicular planes, a living testament to two separate epochs of formation. These rare polar ring galaxies are like cosmic museums, displaying their entire acquisition history in a single, stunning structure. In the mice, we may be witnessing this process in its earliest stages, a ring in the making, offering us a front-row seat to a process that usually takes hundreds of millions of years to complete. It is a perfect example of how the universe often builds its most beautiful structures not from careful design, but from the chaotic, violent, and yet strangely organized aftermath of a collision. Yet, even as we chart the debris of ancient mergers and the orbits of ghostly matter, the Mice Galaxies present us with an object that defies categorization through sheer, raw power, a point of light so brilliant in X-rays that it momentarily outshines the combined output of millions of stars. This is an ultra-luminous X-ray source, or ULX, a cosmic engine that is not the supermassive black hole at the galaxy's core, but something else entirely, blazing with the intensity of 10 million suns all channeled into a single, searing beam of high-energy radiation. Its existence challenges our understanding of how black holes feed and grow, presenting a puzzle with two equally compelling and exotic solutions. The first theory posits that we have found a long-sought cosmic middleweight, an intermediate mass black hole. For decades, astronomers have catalogued black holes in two primary size classes. There are stellar mass black holes, the remnants of massive stars, weighing between 5 and 50 times the mass of our Sun. And there are the supermassive behemoths, millions to billions of times more massive, that anchor galaxies. The space between these classes has been a glaring gap, a missing link in the evolutionary chain. This ULX could be that very missing link, a black hole with a mass of several thousand suns caught in the act of a glorious feast. How would such an object form? The violent environment of the mice provides several dramatic origin stories. It could be the result of dozens of smaller black holes merging together over time within a dense globular cluster, a hierarchical series of cosmic cannibalism that eventually produces a single dominant predator. Alternatively, it could be the collapsed core of a primordial superstar that formed in the early universe under conditions far more extreme than anything possible today. Now, this intermediate mass black hole is devouring a companion star, pulling material from it at a ferocious, unsustainable rate. This kind of feeding frenzy creates an accretion disk of superheated plasma so dense and bright that its radiation pressure actually pushes back against the infalling matter, creating a theoretical limit called the Eddington limit. For a standard stellar mass black hole, this limit would prevent it from ever achieving such incredible luminosity. But an intermediate mass black hole with its stronger gravitational pull could theoretically sustain a higher rate of accretion, allowing it to break through this limit and shine with the monstrous intensity we observe. However, there is a second, more recent theory that is equally fascinating and requires no new class of black hole. This model suggests the engine could be a common stellar mass black hole, but one that is feeding in a uniquely efficient way. Normally, a black hole's accretion disk is a chaotic, turbulent mess, with hot gas glowing brilliantly as it spirals inward. But in certain configurations, if the disk is unusually thick and puffed up, it can form a funnel-like structure at its center, much like the eye of a hurricane. This funnel can then focus and collimate the intense radiation, beaming it out into space in two narrow jets. If one of those jets is pointed almost directly at Earth, we see the full, concentrated force of that energy head-on. The effect is an optical illusion of sorts, a sort of cosmic lighthouse where the beam's intensity is artificially amplified from our specific viewpoint. The black hole itself isn't breaking any fundamental physics. We just have a perfectly aligned seat for its most powerful show. This beam theory elegantly explains the incredible luminosity without requiring us to invent a new type of black hole, though it does demand a very precise and fortunate alignment. Distinguishing between these two models is one of the key goals of modern X-ray astronomy. The telltale clue often lies in the flickering. The X-ray light from a ULX isn't steady. It varies and flickers on timescales from milliseconds to days. The rate of these flickers is tied to the size of the object generating them. A larger black hole has a larger accretion disk, which will vary more slowly, like a large bell ringing with a deeper tone. A smaller black hole's disk will vary more rapidly. By meticulously analyzing the timing of these X-ray pulses, astronomers can effectively take the engine's temperature and estimate the mass of the black hole driving it. Recent observations of some ULXs have revealed incredibly rapid flickering on the order of milliseconds, which strongly supports the stellar mass black hole with a beam model. However, other ULXs show slower, more ponderous variations that still leave the door open for the intermediate mass black hole explanation. The ULX in the Mice Galaxies is still under intense scrutiny, its rapid heartbeat being measured by telescopes like Chandra and XMM Newton, each data point bringing us closer to solving the mystery. What makes this object particularly special within the context of the mice is its location. It is often found not in the quiet outskirts, but within the intense environments of the young superstar clusters we discussed earlier. This is no coincidence. These clusters are the perfect breeding ground for such exotic objects. Their extreme density of massive stars increases the probability of forming black holes and then funneling a companion star into their grasp through gravitational interactions. The ULX is a direct product of the galactic collision, a spectacular and short-lived phase in the life of a binary system that is only possible in the most dynamic and crowded stellar neighborhoods. It represents the pinnacle of stellar violence, a partnership where one star is being consumed to power a beacon of energy visible across millions of light years, a brilliant and temporary testament to the extreme physics unleashed when galaxies collide. Drifting alone in the immense gulf between the two colliding galaxies, far from the brilliant starbursts and sweeping tidal tails, floats a cosmic ghost, a vast, amorphous cloud of gas that at first glance appears to be just another wispy remnant of the collision's violence. But this is no ordinary cloud. When astronomers trained their spectrographs on it, analyzing the specific wavelengths of light it absorbed and emitted, they discovered a chemical fingerprint that was utterly startling. This isolated cloud is incredibly metal-rich. Now, in astronomy, metals mean any element heavier than hydrogen and helium, and this cloud is absolutely brimming with them: oxygen, carbon, nitrogen, iron, and silicon, the very building blocks of planets and life. Its composition is more akin to the crowded interior of a galaxy than to the pristine, primordial gas typically found in intergalactic space. This anomaly makes it a profound and silent witness to the entire life cycle of the Mice Galaxies, long before they ever began their fateful dance. The story of how this cloud became so enriched is a billion-year saga of stellar life and death. Those heavy elements weren't forged in the Big Bang. They were cooked in the nuclear furnaces of massive stars and then violently scattered across space when those stars reached the end of their lives. A first-generation star born from pure hydrogen and helium would explode as a supernova, seeding its local environment with these newly forged metals. The next generation of stars would then form from this slightly enriched gas, living their lives and dying in turn, further polluting the interstellar medium with an even richer mix of elements. This cloud is the product of countless such cycles. Its specific chemical signature, the precise ratios of oxygen to iron, of carbon to nitrogen, acts as a detailed historical record. It tells us that the region it came from experienced vigorous and continuous star formation for billions of years, building up a rich reservoir of complex elements. This wasn't a quiet backwater, it was a thriving stellar metropolis. But how did this metallic treasure trove end up so far from home? The galactic collision provided the catastrophic launch mechanism. During the first few close passes, the gravitational tides acting between the two galaxies would have been immense. They acted like colossal hands, reaching into the galactic disks and grabbing great handfuls of material. While the tidal tails pulled out stars and gas to form the magnificent arcs we see, smaller, denser clumps of gas could have also been ripped loose. This particular cloud was likely once a part of a vibrant spiral arm in one of the original galaxies, a pocket of gas that had been thoroughly enriched by its local stellar population. The gravitational shockwave of the collision then plucked it out and hurled it into the void. A piece of galactic infrastructure suddenly set adrift. Its journey since then has been one of quiet isolation, expanding and cooling as it travels through the near-perfect vacuum of intergalactic space. Its current solitude makes it an invaluable natural laboratory. Shielded from the frenetic energy of the ongoing merger, its chemistry is no longer being altered by new supernova or the radiation from young, hot stars. It is a perfectly preserved sample, a snapshot of the galactic ecosystem frozen in time at the precise moment it was ejected. By studying its composition in minute detail, astronomers can perform a kind of cosmic archaeology, working backwards to understand the star formation history of the progenitor galaxy. The amount of oxygen present, for instance, tells us about the number of very massive, short-lived stars that must have existed, as oxygen is primarily produced in their explosions. The iron content, on the other hand, builds up more slowly over time from a different type of supernova, indicating a long, sustained period of stellar death. This single cloud allows us to reconstruct the evolutionary timeline of an entire galaxy, a story that would otherwise be lost amidst the chaos of the merger. The ultimate fate of this metallic cloud is a slow and cold one. Devoid of the external pressure and triggers found within a galaxy, it is unlikely to collapse and form new stars on its own. It will likely continue to drift for billions of years, its atoms gradually dispersing into the intergalactic medium. In a way, this is how the universe enriches itself on the largest scales. These ejected clouds are the mechanism by which the heavy elements forged in galactic interiors are eventually distributed into the vast voids between galaxies, seeding the cosmos with the potential for rocky planets and perhaps one day life. This unassuming cloud is therefore more than just a relic. It is a vital courier carrying the legacy of a billion dead stars out into the darkness, ensuring that their cosmic contribution is not confined to a single galaxy but becomes a part of the universal tapestry. While the collision of the Mice Galaxies plays out as a spectacular visual drama, it is also generating a deeper, more fundamental vibration, a tremor in the very fabric of reality itself that we are only just beginning to learn how to detect. The primary source of this cosmic shudder is the slow, inevitable dance of the two supermassive black holes at the galaxy's hearts. As they spiral closer and closer, their immense masses whipping around each other at a significant fraction of the speed of light, they do not move silently through space. Instead, they lose energy by radiating it away in the form of gravitational waves, ripples in the fabric of space-time that propagate outward at the speed of light in all directions. Each pair of inspiraling supermassive black holes in the universe contributes its own unique tone to this cosmic symphony. The frequency of the gravitational waves they produce is directly tied to their orbital period. For stellar mass black holes just seconds from collision, like those detected by LIGO, the waves are a high-pitched chirp, ringing in the range of hundreds of cycles per second. But for supermassive giants like those in the Mice, which take years or even decades to complete a single orbit, the waves they generate are incredibly low frequency, with wavelengths so long they could span entire solar systems. These are not chirps, they are a deep, resonant hum, a bass note in the cosmic chorus that is far too low for Earth-based detectors to hear. This is where the concept of the stochastic gravitational wave background comes into play. Imagine standing in a crowded room where every single person is having a separate conversation. You cannot make out any single discussion, but you are surrounded by a constant, indistinct murmur, a background hum of human noise. The universe is like that room. Countless pairs of supermassive black holes from merging galaxies all across cosmic history are constantly generating their own low-frequency gravitational waves. The combined effect of all these overlapping signals creates a persistent, all-pervading hum that fills the entire universe. This is the gravitational wave background, and the Mice Galaxies are one active, contributing voice in that immense choir. Detecting this background hum is one of the grandest challenges in modern physics, requiring a telescope of an entirely different sort. Ground-based observatories like LIGO and Virgo are exquisitely tuned to hear the high-frequency crashes of stellar mass objects, but they are utterly deaf to the low-frequency rumble of supermassive binaries. To hear that, we must go to space. Future missions like the Laser Interferometer Space Antenna, or LISA, are designed specifically for this purpose. LISA will consist of 3 spacecraft flying in a vast triangular formation millions of kilometers apart, connected by lasers. By precisely measuring the minute changes in distance between these satellites, changes smaller than the width of an atom, it will be able to sense the subtle stretching and squeezing of space-time caused by passing low-frequency gravitational waves. The contribution from systems like the mice is crucial because they represent a nearby, well-studied example of the phenomenon that creates this background. By understanding the masses, separation, and orbital dynamics of the black holes in the mice, astronomers can better model the precise waveform they should be producing. This allows them to refine the templates they will use to sift the faint, specific signal of a binary in spiral from the overwhelming stochastic noise of the universal hum. It turns the mice from a distant spectacle into a vital calibration source, a known reference point that helps us interpret the data from future observatories. Hearing this cosmic murmur would open an entirely new window onto the universe. It would allow us to take a census of the most massive objects in the cosmos throughout time, revealing the history of galaxy mergers and the growth of supermassive black holes. It could even provide insights into the very nature of gravity and spacetime itself, testing the limits of Einstein's theory under the most extreme conditions. The silent, invisible dance at the heart of the Mice Galaxies is therefore not just a local event. It is a thread woven into the deepest fabric of the cosmos, a vibration that connects this one collision to the grand, unfolding story of the entire universe. At the very heart of this cosmic collision, a silent countdown may be underway, one that could unleash the single most powerful and sustained energy source in the known universe. The two supermassive black holes we've discussed are not just dancers, they are potential engines of unbelievable power, and astronomers are watching them closely for signs that they are about to awaken in a spectacular way. The theory is that the ongoing merger is in the process of funneling a truly staggering amount of gas directly into the grasp of these gravitational monsters, potentially setting the stage for a quasar ignition event, a transformation that would turn the galactic core from a powerful engine into the brightest beacon for millions of light years. For a quasar to ignite, a supermassive black hole needs a constant, massive, and dense supply of gas. This isn't about a few stars falling in. It requires the equivalent of consuming 10 or more suns worth of material every single year. This gas can't fall directly into the black hole because of its angular momentum. Instead, it piles up into a vast, whirling structure called an accretion disk. As this disk spins at nearly the speed of light, the particles within it smash together, creating immense friction. This friction heats the gas to temperatures of millions of degrees, causing it to glow with a blinding intensity that can outshine the entire galaxy that hosts it. This is the heart of a quasar, an accretion disk so brilliant and energetic that it turns the black hole's immediate surroundings into the most luminous object in the universe. The merger of the Mice Galaxies is essentially creating the perfect storm for this to happen. The violent gravitational tides are shaking loose vast reservoirs of cold gas from the spiral arms and funneling them inexorably toward the center. Furthermore, the black hole binary itself acts as a chaotic pump, stirring up the central region and ensuring that a significant fraction of this gas loses its angular momentum and spirals inward rather than settling into orbit. It's the cosmic equivalent of throwing logs onto a dormant fire. Eventually, you add enough fuel to create a roaring blaze. Astronomers are searching for specific telltale signs that this ignition is imminent or has just begun. They are looking for a dramatic and sustained increase in brightness across multiple wavelengths, but especially in ultraviolet and X-ray light, which are the primary signatures of a superheated accretion disk. They are also monitoring for the emergence of powerful, narrow jets of plasma that can sometimes be launched from the poles of the feeding black hole, beams of energy that travel at nearly the speed of light and can stretch far beyond the confines of the galaxy itself. Catching this event in the act would be a monumental discovery. It would allow us to witness in real time the awakening of a cosmic titan and study the entire life cycle of a quasar from its very first moments. We could watch how the outpouring of energy affects the rest of the galaxy, potentially quenching star formation by blowing away the remaining gas or, conversely, triggering new waves of birth by compressing distant clouds. It would provide an unprecedented laboratory to study the most extreme physics of accretion and relativity, happening right on our cosmic doorstep. The central region of the Mice is now a watched pot, and astronomers are waiting with bated breath to see if it will finally boil over into one of the most dazzling shows the universe has to offer. Yet as the central black holes dance and the galaxies swirl, another kind of formation is taking shape on a scale that dwarfs our own solar system. Deep within a brilliant superstar cluster, a stellar newborn of staggering proportions is settling into its life, and surrounding it is a whirlwind of primordial material so vast it redefines what we thought was possible. This is a debris disk giant, a young, massive star encircled by a colossal disk of rock, ice, and dust that stretches for hundreds of billions of miles. To call it a debris disk is almost a misnomer. This isn't just the leftover crumbs from the star's formation. It is a full-blown cosmic construction zone, a chaotic, vibrant arena where the next chapter of this galactic story, the birth of planets, is just beginning. The star at the center of this maelstrom is itself a behemoth, many times more massive and infinitely brighter than our own sun. It burned through its initial fuel of surrounding gas with ferocious speed, and now its powerful radiation and stellar winds are blowing the remaining nebula clear, leaving behind this immense flattened disk of cooler material. But unlike the relatively serene protoplanetary disks we see around smaller stars, this one is a site of incredible violence and activity. Within the disk, countless particles, from fine dust grains to mountain-sized boulders, are constantly smashing into each other. Some collisions are gentle, allowing fragments to stick together through static electricity in a process called accretion. But many are catastrophic, shattering larger bodies back into smaller pieces in a relentless cycle of creation and destruction. This is the collisional cascade that gives a debris disk its name, a grinding mill that turns asteroids into dust and dust into the fine particulate that glows faintly in the infrared. What makes this particular disk an object of such intense fascination is its sheer, almost incomprehensible scale. The most massive debris disk we know of in our own galaxy, around the star Beta Pictoris, is a spectacular sight, but it is a mere trinket compared to the disk encircling this stellar giant in the Mice. This structure contains enough solid material to form not just a few rocky planets, but dozens of Earths, perhaps even several Jupiter-sized worlds. The sheer volume of raw ingredients is staggering, suggesting that if planet formation can successfully navigate the turbulent environment here, the resulting planetary system would be of a scale and complexity we can hardly imagine. We could be looking at the blueprint for a solar system that would make our own appear quaint and minimalist by comparison. The potential for such a system is both thrilling and fraught with peril. The environment around a massive star is notoriously hostile to planet formation. The intense ultraviolet radiation from the star bombards the disk, threatening to vaporize ices and blow away lighter gases before they can coalesce into the cores of giant planets. The very gravitational interactions that are herding particles together into larger bodies can also be their undoing, as the constant jostling from nearby stars in the dense cluster can destabilize orbits and fling budding planets into the void or send them careening into their parent star. It's a high-stakes game where the rewards, a vast, sprawling family of worlds, are matched by the extreme challenges of building them in a celestial war zone. Yet, the very presence of this massive, persistent disk is a testament to the tenacity of the planet-forming process. It suggests that even in the most chaotic and energetic environments, the fundamental drive to assemble order from chaos persists. Within this swirling tempest of rock and ice, the first planetesimals, the building blocks of planets, are likely already forming. These kilometer-sized chunks of material are the crucial intermediate step between dust and planets, the seeds from which entire worlds will grow over the next hundreds of millions of years. Their growth is a race against time, a battle to achieve enough mass to hold onto their own gravitationally bound atmospheres before the radiation from their brilliant parent star strips everything away. Observing this disk is like looking back into the deepest past of our own solar system, but with the volume turned up to an 11. It provides a unique laboratory to test our theories of planet formation under the most extreme conditions. By studying its structure, its composition, and its dynamics, we can learn not only about the potential for new worlds in the Mice Galaxies, but also about the universal processes that govern the birth of every planetary system. This colossal disk is more than just a cloud of debris. It is a promise of things to come, a potential future filled with unknown worlds waiting to be born from the aftermath of a galactic collision. Stretching out from the chaos of the galactic core, the magnificent tidal tails of the Mice Galaxies have long been celebrated for their visual drama, the graceful arcs of exiled stars, the brilliant blue clusters of newborn suns. But recent observations have uncovered a hidden architecture within this apparent chaos, a force operating on an immense scale that is silently shaping the destiny of this expelled material. Using sophisticated radio telescopes, astronomers have mapped the magnetic fields within one particular tidal tail and found something that defies expectation: a strangely ordered, powerful, and coherent magnetic field running like a cosmic backbone along the entire length of this stellar river. In a region where matter has been violently ripped loose and flung into the void, such a strong and uniform structure is profoundly unexpected. It suggests that the forces at play in a galactic collision are even more complex and fascinating than we imagined, weaving an invisible tapestry of influence that guides the flow of gas and the very birth of new stars. To understand why this finding is so surprising, we need to consider the nature of these tidal tails. They are the result of extreme gravitational violence, regions where the fabric of the original galaxies has been pulled and stretched beyond recognition. You would expect the magnetic fields within this disorganized debris to be equally chaotic, tangled, weak, and fragmented, like a ball of yarn after a cat has played with it. The discovery of a strong, well-ordered field means that some process is actively generating and organizing magnetic energy within the tail itself, imposing order on the disorder. This process is known as dynamo amplification, and it is turbocharged by the conditions of the merger. As the vast clouds of gas are pulled out, they are not moving smoothly, they are shearing, spinning, and turbulent. This motion, especially when it involves ionized gas that can conduct electrical currents, can stretch and twist weak, pre-existing magnetic field lines, dramatically amplifying their strength. It's the cosmic equivalent of rolling a ball of string down a hill. The motion itself untangles and stretches it into long, coherent lines. The incredible turbulence of the collision essentially acts as a giant magnetic dynamo, generating a powerful and surprisingly organized field from the initial chaos. This newly forged magnetic field is far from a passive bystander. It becomes an active player in the ongoing evolution of the tail. Think of it as a set of invisible railroad tracks laid down through the darkness of intergalactic space. The field lines act as channels, guiding the flow of ionized gas and preventing it from simply dissipating into the void. They can funnel material along specific paths, helping to gather and concentrate the gas into denser clumps. This is a crucial step in the star formation process. For a cloud of gas to collapse under its own gravity and ignite into a new star, it must first reach a critical density. The magnetic field provides the scaffolding that makes this gathering possible, herding the raw materials together into stellar nurseries. Furthermore, a strong, ordered magnetic field can also help support a gas cloud against its own gravity long enough for it to build up sufficient mass, regulating the pace of star birth and potentially influencing the ultimate size and number of the stars that form. In the brilliant superstar clusters we see dotted along the tail, We are likely witnessing the direct result of this magnetic guidance. The fields helped concentrate the gas that led to these spectacular bursts of creation. The presence of this magnetic anomaly also offers a potential solution to another puzzle of the mice: how these incredibly massive, dense star clusters manage to form so far from the stabilizing gravitational influence of a galactic core. The magnetic field could provide the necessary additional support and structure, acting as a substitute anchor that allows these colossal structures to assemble themselves in the relative emptiness of intergalactic space. It's a stunning reminder that the universe builds with more than just gravity. It uses every tool in its kit, including fundamental forces that are completely invisible to our eyes. This discovery transforms our view of the tidal tales from simple streams of exiled matter into dynamic, organized structures, where magnetic fields serve as the invisible architects, quietly directing the construction of new suns and cities of stars in the deep darkness between galaxies. But the evidence for a more dramatic history is written in the stars themselves, in a language of light that astronomers have learned to decipher. This isn't just a random cluster, it's a living archaeological site. The key to its past lies in metallicity, the abundance of elements heavier than hydrogen and helium within its stars. In the cosmic timeline, the first stars to form after the Big Bang were composed of almost pure hydrogen and helium, the primitive elements forged in the universe's first moments. They lived fast, died young, and exploded as supernova, seeding their surroundings with the first heavy metals: carbon, oxygen, iron. The next generation of stars formed from this slightly enriched gas, and so on, with each stellar birth cohort having a progressively higher metal content. A star's metallicity is therefore a cosmic birth certificate, telling us roughly when it was born. The stars in this dense cluster are remarkably uniform in their ancient metal-poor composition. They are cosmic relics, all forming within a very short period of time, over 10 billion years ago, from gas that had seen very little prior enrichment. This is the classic signature of a dwarf spheroidal galaxy, a small, primitive building block of the universe. These galaxies are thought to be the first structures to coalesce after the Big Bang, and their simple, inefficient star formation means they never produced enough subsequent generations to significantly pollute their environment with metals. This cluster's stellar population is a perfect match, a preserved sample of the early universe that has been delivered to our doorstep by the violent mechanics of the Mice merger. By dating these ancient stars, astronomers can pin a timestamp on the original act of cannibalism, determining that this dwarf galaxy was consumed not during the current collision, but in a much earlier, quieter merger event that happened billions of years ago. This single, dense knot of stars therefore tells a profound story about how galaxies grow. We don't build giant spirals like the Milky Way or the original mice from scratch. We build them hierarchically through a long history of mergers and acquisitions. Large galaxies are like cosmic corporations, growing over time by absorbing smaller competitors. This cluster is the surviving corporate logo on a faded briefcase, the last remaining piece of a smaller company that was fully integrated long ago. Its current chaotic orbit within the mice is the final chapter of that ancient takeover, a gravitational echo of a meal consumed eons past. It serves as direct, observable proof that the Mice Galaxies were already large and dominant structures long before they ever found each other. Their current spectacular collision merely the latest in a long series of galactic growth spurts that began not long after the dawn of time itself. Out in the profound darkness between the two colliding galaxies, far from the dense star fields and glowing nebulae of the spiral arms, a different kind of violence has left its mark. This is the shell of a star that died alone. Designated as Object 25, it is the expanding remnant of a supernova that detonated not within the safe confines of a galactic disk, but out in the isolated vastness of the tidal tail or the intergalactic hydrogen bridge. Its discovery was a surprise. Supernovae are expected to occur within galaxies where massive stars are born. Finding one out here, in what was thought to be a near-perfect vacuum, forces us to reconsider the very conditions needed for such a cataclysmic death. The environment of this explosion is unlike any other we've studied. Within a galaxy, a supernova's blast wave slams into the surrounding interstellar medium, a fog of gas and dust that, while thin by our standards, is dense enough to dramatically slow the explosion's expansion. This interaction creates the brilliant, complex, and often beautiful nebulae we're familiar with, like the Crab Nebula, which glow across the electromagnetic spectrum as the shock front heats the surrounding material to millions of degrees. But out here in the intergalactic void, the medium is almost unimaginably sparse. The density of particles can be 1,000,000 times lower than inside a galaxy. It is the difference between setting off a firecracker in a crowded city square and setting one off in the middle of a vast, empty desert. This profound difference in environment dictates the entire life story of this remnant. Without a significant external medium to push against, the initial blast from the supernova would have expanded WITH Chinese letter Chinese letter Chinese letter Chinese letter Chinese letter Chinese letter, its shell of stellar debris flying outward at thousands of kilometers per second for much longer than it could within a galaxy. Instead of forming a classic rounded nebula, the remnant might maintain a much more spherical and simple structure for eons, a nearly perfect bubble expanding into nothingness. The lack of material also means there is very little to get heated up and glow. This remnant would be incredibly faint in visible light and X-rays, explaining why it remained hidden for so long. It was likely discovered through its very faint radio emissions, generated by high-energy electrons spiraling in the weak magnetic fields that were stretched out into the tidal tail, or by catching the faint echo of its light as the initial flash from the supernova itself illuminated a passing cloud of gas years after the event. The very existence of this intergalactic supernova tells a dramatic story about stellar life and death in extreme environments. The star that created it was not born out here in the darkness. It was born within one of the brilliant superstar clusters that formed in the tidal tail during the initial stages of the collision. This massive star lived its short, intense life within that dense cluster. But then, the same gravitational chaos that created its birthplace likely also sealed its fate. A close encounter with another star within the cluster could have gravitationally slingshotted it out, ejecting it into the void as a runaway star. It then spent the remaining few million years of its life traveling through the emptiness, a solitary giant marching toward its doom, until its core finally collapsed and it exploded, lighting up the intergalactic night with a flash that had no audience but the cold, empty space around it. Studying this lonely remnant offers a unique opportunity for astronomers. Because it is expanding into such a negligible medium, its dynamics are governed almost purely by the physics of the initial explosion itself. By carefully measuring its expansion rate and structure, scientists can work backwards to calculate the precise energy of the supernova blast and the amount of mass that was ejected, getting a much cleaner reading than is possible with remnants mudded by interaction with complex galactic environments. It acts as a pure laboratory for studying supernova mechanics. Furthermore, its long, unimpeded journey allows its expanding shell to act as a probe. As it grows, it will eventually encounter the tenuous gas of the intergalactic bridge. By watching how the remnant's expansion subtly changes when it begins to interact with this gas, we can finally measure the density and pressure of this elusive material directly, something that is nearly impossible to do otherwise. This solitary shell of debris, the ghost of a star that died far from home, has become an unintentional scientific instrument, helping us map the true emptiness of the space between galaxies. But how do we find something that emits no light of its own, drifting in the profound darkness between stars? The answer lies in a phenomenon predicted by Einstein's theory of general relativity, a celestial magic trick that allows the invisible to briefly reveal itself. This is gravitational microlensing, and in the crowded star fields of the Mice Galaxies, it creates a specific telltale signal that astronomers have learned to hunt: a temporary, symmetrical brightening of a distant star, a flicker of light that acts as the signature of a hidden mass passing through our line of sight. It is the universe's most subtle form of shadow puppetry, where the puppeteers are the strange, dark objects themselves, and the screen is the fabric of space-time. The mechanics of this effect are beautifully elegant. Any object with mass warps the space around it. When one of these dark, planetary mass wanderers drifts almost perfectly between Earth and a much more distant background star, its gravity acts as a tiny lens. It bends and focuses the light rays from that background star, causing the star's image to briefly brighten. The alignment has to be nearly perfect to produce an effect we can detect, which makes each event incredibly rare. From our perspective, the background star will appear to slowly brighten to a peak and then fade away in an almost perfectly symmetrical curve over a period of hours or days. The duration of this light curve is the first major clue. A Jupiter mass object will create a longer, drawn-out brightening than an Earth mass object, simply because its gravitational influence stretches across a wider area of space, keeping the lensing alignment for a longer time. The shape and precise details of the curve can even hint at whether the lensing object is alone or has its own moons, adding another layer of complexity to the detective work. For astronomers, each of these microlensing events is a precious data point in a vast cosmic census. The primary goal of large-scale surveys monitoring the mice is to determine just how many of these dark, wandering bodies were created by the galactic collision. Every time a star flickers in this specific way, it's not just a curiosity. It's a direct detection of a single object that would otherwise be completely invisible. By counting these events over time, scientists can begin to build a statistical picture of this hidden population. They can estimate the total number of rogue planets, cold white dwarfs, and isolated neutron stars that were gravitationally purged from their home systems and flung into the void. The frequency of these events tells us if the collision generated a sparse scattering of exiles or a veritable fog of dark worlds, a finding that has huge implications for understanding the efficiency of galactic mergers at disrupting planetary systems. The value of this technique goes far beyond mere counting. The specific nature of the lensing event can sometimes reveal the approximate mass of the object causing it, allowing us to categorize it. A very short duration flicker points to a low-mass object, likely a rogue planet. A longer, more pronounced event could indicate a white dwarf or even a neutron star. This allows researchers to not just count the population, but to inventory it to understand the different classes of objects that make up this unseen diaspora. It transforms the invisible into the quantifiable. Yet, observing these events in the mice presents a unique set of challenges and opportunities. The distance to the mice means the background stars being lensed are incredibly faint to begin with, requiring the immense light-gathering power of the world's largest telescopes and the relentless monitoring of space-based observatories. However, the incredible density of stars within the merging galaxies works in our favor. With so many potential background sources, the probability of catching these rare alignments while still low is significantly higher than it would be in a quieter, more isolated galaxy. It's the cosmic equivalent of looking for a rare animal. You'll have better luck in a dense rainforest than in an empty desert. The chaotic environment of the mice, which created these dark wanderers, also provides the perfect crowded backdrop against which to find them. Each successful detection is a small triumph of patience and precision, a single point of light on a vast graph that slowly, painstakingly, charts the invisible architecture of the galaxy. These microlensing flickers are more than just data. They are the fleeting glimpses of a hidden reality, proof that our universe is filled with ghosts, the cold, dark and lonely remnants of stellar systems shattered by a violence that occurred millions of years ago, their presence only betrayed by the way they bend the light of stars they will never know. Amidst the swirling chaos of gas and newborn stars, the Mice Galaxies host a natural amplifier of such precision and power that it transforms a cloud of molecules into a cosmic lighthouse, broadcasting its presence across the universe on a specific, narrow frequency. This is an OH megamesa, a phenomenon where a cloud of hydroxyl molecules, simple pairs of oxygen and hydrogen atoms, becomes a natural laser, but for microwave radio waves. The mega in its name is no exaggeration. This is not a subtle signal. It outshines any similar maser emission from within our own Milky Way by a factor of millions, a brilliant beacon shining in a very specific part of the radio spectrum that cuts through the cosmic noise with astonishing clarity. The creation of this microwave spotlight requires a very specific and extreme environment, a recipe that the Mice Galaxies provide in abundance. It begins with the intense ultraviolet radiation pouring from thousands of newly formed massive stars within one of the superstar clusters. This brutal radiation pumps energy into the vast, dense molecular clouds surrounding the cluster, exciting the hydroxyl molecules within them. But the real magic happens through a process called stimulated emission. Imagine a lone, excited hydroxyl molecule eventually relaxing and emitting a photon of a specific microwave frequency. If that photon then travels through the cloud and strikes another excited hydroxyl molecule, it doesn't just bounce off. It triggers that second molecule to emit an identical photon, perfectly in sync with the first. This process starts a chain reaction, a cascade of identical photons all moving in the same direction, at the same frequency, and in perfect phase. The cloud itself acts as the resonator, with dust grains often serving as the mirrors that bounce the photons back and forth, amplifying the signal until it bursts forth as a coherent, incredibly powerful beam of microwave radio waves. It's a natural version of the laser technology we use on Earth, but operating on a galactic scale and with unimaginable power. This makes the megamesa far more than just a cosmic curiosity. It is one of the most valuable precision tools in an astronomer's toolkit for studying a chaotic system like this merger. Because the emission is so perfectly monochromatic, all concentrated at one exact frequency, any shift in that frequency is immediately obvious and incredibly easy to measure. This shift is caused by the Doppler effect. As the cloud of gas hosting the megamesa moves toward us or away from us along our line of sight, its entire microwave beam is shifted to a slightly higher or lower frequency, much like the pitch of a siren changes as an ambulance races past. By measuring this precise Doppler shift, astronomers can calculate the exact velocity of that cloud with an accuracy that is simply impossible with broader, messier sources of light. We can track the motion of individual gas clouds within the frenzy of the collision, mapping the complex flows and turbulence with exquisite detail. It allows us to see which parts of the gas are falling inward, which are being flung outward, and how these motions are shaped by the invisible hand of dark matter. Furthermore, this pinpoint precision makes the OH megamesa a potential key to solving one of the greatest challenges in cosmology, measuring precise distances to faraway galaxies. In astronomy, measuring distance is everything, but it's notoriously difficult. The megamesa method is beautifully direct. By observing a megamesa disk that is oriented edge onto us, often around the very central supermassive black hole, astronomers can use a technique called interferometry to map the individual spots of maser emission within the disk. Some of these spots will be on the side of the disk rotating toward us, some on the side rotating away from us. By combining the Doppler shift velocities with the physical separation of these spots on the sky, scientists can directly calculate the distance to the galaxy through simple geometry, a method known as direct mapping. It's like surveying a plot of land with a theodolite, but on a galactic scale. A single, well-studied megamesa can provide a cosmic yardstick of unparalleled accuracy, helping to calibrate the entire distance ladder of the universe and refine our measurement of the Hubble constant, the rate of the universe's expansion. In the tumultuous heart of the Mice, this brilliant microwave beacon does more than just signal intense star formation. It provides a steady, precise voice of clarity amidst the roar, offering a unique window into the dynamics and very scale of the cosmos itself. Early in the observations of the Mice, a fascinating puzzle presented itself at the heart of one of the spirals. In lower resolution images, the core region didn't appear as a single, bright point. Instead, it seemed to be split, presenting astronomers with what looked like a double nucleus, two distinct, bright sources nestled close together in the galaxy's chaotic center. This was an electrifying prospect. A double nucleus could indicate a spectacular scenario: two supermassive black holes, each the anchor of its own original galaxy, now orbiting each other so closely that they were both visible as separate entities. It seemed like the ultimate confirmation of the merger's progress, a direct snapshot of the central engine coming together. However, the universe often guards its secrets behind layers of complexity, and this apparent duality was a perfect example of a cosmic illusion. The advent of powerful, high-resolution telescopes like the Hubble Space Telescope and later the James Webb Space Telescope completely changed the story. When they turned their sharp eyes toward this double heart, they resolved the blur into its true components. One of the bright points was indeed the true galactic nucleus, home to the supermassive black hole and its brilliant accretion disk. But the other, it wasn't a black hole at all. It was revealed to be an incredibly massive and dense star cluster, a spectacular superstar cluster that had formed so close to the galactic center that its collective light rivaled the output of the core itself. From our distant vantage point, the two had been blurred together into a single, misleading image. This case study is a humbling reminder of the challenges inherent in observing the distant universe. When we look at objects millions of light-years away, we are often viewing crowded fields where countless stars, clusters, and structures are compressed into a tiny area of the sky. Our perspective is flat, we cannot perceive depth. A star cluster that is actually many light-years in the foreground or background of the true core can appear to be right beside it, creating a projection effect that can easily fool us. It's the astronomical equivalent of seeing two fireflies close together from a mile away. You cannot tell which is actually closer to you. Without the resolving power to separate these objects, we are left to interpret the blur, and sometimes our interpretations, while logical, can be completely wrong. The resolution of this illusion underscores a critical truth in modern astronomy. You cannot believe everything you see at first glance. This is why the continuous development of ever-sharper telescopes is so vital. Each leap in resolution peels back another layer of cosmic disguise, allowing us to replace educated guesses with definitive observations. The correction from a double nucleus to a nucleus and cluster pairing also forced a significant recalibration of our models for this merger. It meant the central black hole binary might be at a different stage of its inspiral than we first thought, and it highlighted the astonishing ability of these collisions to form monstrous star clusters even in the most extreme gravitational environment imaginable, right on the doorstep of a supermassive black hole. This one correction, born from clearer vision, refined our entire understanding of the dynamics at the very heart of the collision. While the chaotic dance of the two galaxies dominates the scene, a different kind of impact may be occurring on the outskirts, a silent, high-speed collision with a ghost from the deepest voids. Drifting through the unimaginable emptiness of intergalactic space are vast, dark clouds of primordial gas, remnants from the formation of the cosmic web itself. These high-velocity clouds are cosmic nomads, and one such traveler may now be on a direct collision course with the already beleaguered disk of one of the Mice Galaxies. Unlike the slow, gravitational merger of the two spirals, This would be a high-speed impact, a bullet of cold gas slamming into the galactic plane at hundreds of kilometers per second. The telltale signature of such an event wouldn't be a graceful tidal tail, but a violent, localized splash of star formation, a brilliant and sudden scar on the face of the galaxy. The origins of this high-velocity cloud are ancient, tracing back to the very structure of the universe. It is part of the vast filamentary cosmic web, a river of pristine hydrogen and helium that flows through the darkness between galaxy clusters. This cloud is likely a fragment that was stripped away during the formation of the local galaxy group eons ago. Or perhaps it is a cloud that never managed to collapse into a galaxy at all, remaining a free-floating reservoir of unused building material. For billions of years, it has drifted undisturbed, its atoms never feeling the heat of a star, its composition unchanged since shortly after the Big Bang. Its journey is now bringing it into the gravitational sphere of the mice, and its high speed suggests it is not bound to the system. It is a first-time visitor, a cosmic comet making a single dramatic pass. When this massive cloud, which could contain the mass of 1 million suns, plows into the galactic disk, the result is a spectacular shockwave. The incoming cloud, though diffused by terrestrial standards, is still far denser than the thin halo of hot gas that surrounds a galaxy. As it rams into this halo and then into the denser disk material, it creates immense pressure at the leading edge of the impact. This pressure violently compresses the cloud itself along with any interstellar gas it encounters, triggering a frantic and localized burst of star formation. From our perspective, we wouldn't see a spreading ring or a spiral arm lighting up. Instead, we would see a brilliant, somewhat irregular knot of young, blue stars appearing almost out of nowhere on the galactic periphery, a starburst splash zone marking the point of impact. The morphology would be distinct from the organized clusters in the tidal tails. This would look more like a fiery blossom or a spray of stellar embers kicked up by the collision. This process is a dramatic form of what astronomers call cold mode accretion, a vital way for galaxies to gather fresh fuel and grow throughout their lives. While the major merger of the two Mice Galaxies is providing a colossal, one-time injection of gas and triggering immense internal star formation, the impact of a high-velocity cloud represents a smaller, more frequent top-up of pristine raw materials. It's the difference between a huge inheritance and a steady, unexpected bonus. This incoming gas is unenriched by previous generations of stars. It is pure hydrogen and helium, the fundamental ingredients of the universe. When it ignites into new stars, those stars will be metal poor compared to their cousins formed from the galaxy's own recycled gas, providing a new population with a unique chemical signature. Observing such an event in the mice would be a rare opportunity to study this accretion process in real time. By measuring the velocity and composition of the gas in and around the splash zone, astronomers could directly track how the intergalactic medium mingles with the galactic disk. They could watch how the shock front propagates and how efficiently it converts gas into stars. It would show us that a galaxy is not an isolated island universe, but a dynamic structure that is continually interacting with its environment, gathering new material from the cosmic flows that connect all things. Even as the mice engage in their own epic dance, they remain part of the broader cosmic ballet, open to influences from the vast, dark ocean of space that surrounds them. And now we arrive at the final object on our list, the one that perhaps best embodies the spirit of this entire journey. A profound mystery that sits at the very edge of our understanding, an anomaly that invites our wildest speculations while demanding our most rigorous skepticism. This is Object 30, a point source of light within the mice that emits a spectrum of energy so unusual, so unlike anything we typically observe in nature, that it forces us to confront a thrilling and daunting question. Are we looking at an incredibly rare yet natural astrophysical process we've never witnessed before, or could we be seeing something else entirely? This is the realm of technosignatures, the search for potential signs of technology beyond Earth, and it is a field where extraordinary claims require not just extraordinary evidence, but an extraordinary process of elimination first. Let's be unequivocally clear from the outset. The absolute null hypothesis, the default assumption that must be disproven beyond a reasonable doubt, is that this is a natural phenomenon. The history of astronomy is littered with exciting anomalies, from the pulsars initially nicknamed LGM for little green men to more recent curiosities that were eventually explained by new and fascinating physics, not extraterrestrial engineers. The scientific protocol is methodical and strict. Every possible natural explanation must be exhausted before any other possibility can be seriously entertained. So what makes this particular point source so intriguing? Its emission spectrum contains a combination of features that are deeply puzzling. It might exhibit an extremely narrow, intense spike at a specific frequency, a signature of highly coherent light that is very difficult to produce naturally over such astronomical distances. Or perhaps it shows a combination of spectral lines indicating molecules that are unstable or rare in space, arranged in a pattern that suggests they are not in thermal equilibrium, not mixed as nature would typically leave them. It could even be flickering or modulating in a complex, non-repeating pattern that doesn't match the predictable rhythms of pulsars or other variable objects. It's this combination of oddities, this violation of several expected astrophysical rules simultaneously, that places it in a special category of curiosity. The first and most important step is to search for a natural engine that could power such a strange beacon. Could this be an utterly novel form of pulsar, one with a magnetic field configuration or accretion mode we haven't yet theorized? Perhaps it's the signature of an exotic chemical reaction occurring on the surface of a frigid, dark world far from any star, a geological process playing out on a continental scale. Maybe it's the light echo of a one-time cataclysmic event, like a hypernova or a quark nova, whose afterglow properties we simply haven't had the chance to study before. Another compelling possibility is that we are seeing the interaction of a high-energy particle jet with a previously unknown type of interstellar medium, a collision that produces a unique and temporary spectroscopic fingerprint. The chaotic environment of the Mice, a galactic pressure cooker, is the perfect place for such rare and short-lived natural events to occur. The merger is creating conditions that don't exist in quieter galaxies, and therefore it is the most likely place to discover new classes of astrophysical objects. This anomaly is probably the first of its kind simply because the conditions to create it are so exceptionally rare. Yet, it is the very duty of science to ask the next question, to follow the evidence wherever it may lead, no matter how improbable the destination. And this is where the concept of a technosignature carefully enters the conversation, not as a conclusion, but as a potential boundary of what we might one day discover. A technosignature is any measurable property that provides evidence of technology. Unlike the search for radio signals or laser pulses, which are often called active SETI, this is a search for passive evidence, the unintended byproducts or immense artifacts of an advanced civilization. Think of it not as a message meant for us, but as the inevitable energy signature of a society operating on a scale we can barely imagine. For a civilization far more advanced than our own, their energy needs would be astronomical. They might harness the total output of their star with a Dyson swarm, a vast collection of energy collecting satellites that would radiate waste heat as a distinctive infrared signature. They might propel spacecraft at a significant fraction of the speed of light using powerful laser beams, whose light could appear as a temporary, ultra-bright point source exactly like the one we're seeing. Or they might be engaging in large-scale astroengineering, attempting to stave off a future supernova or modify their stellar environment, processes that would undoubtedly leave a complex and unnatural-looking mark on the spectrum of their star. This is the ultimate thought experiment that an object like this provokes. It forces us to consider intelligence not just as a biological phenomenon, but as a potential geological and astronomical force, one that could reshape the fundamental appearance of a galaxy over millions of years. The time frame of the Mice Galaxies is crucial here. The light we are seeing from this object left on its journey to Earth 300 million years ago. If this were evidence of a technology, it would be a snapshot of a civilization that existed and perhaps vanished long before life on Earth had even crawled out of its primordial oceans. We would not be detecting a signal meant for us. We would be uncovering a cosmic archaeological relic, the ghost of an empire that rose and fell in the deep time of another galaxy. The sheer scale of such a thought is enough to send a shiver down one's spine. So how does science proceed from here with intense curiosity, but also with immense patience and humility? The next steps are not wild speculation, but meticulous observation. Astronomers will point every available telescope, from radio dishes to gamma-ray observatories, at this point of light for thousands of hours, collecting every possible photon. They will look for periodicities, for subtle changes in the signal, for any clue that might reveal the underlying mechanism. They will search for other, similar objects in other merging galaxies to see if this is a unique event or a repeatable phenomenon. Most importantly, they will tirelessly work to develop new natural astrophysical models that can account for every strange feature of the emission. The greatest discovery would not be confirming it as a technosignature. The greatest discovery would be uncovering a completely new law of physics or a new type of celestial object that explains it naturally. That in itself would revolutionize our understanding of the universe. This object, this final mystery in our list of 30, is therefore a perfect symbol for our relationship with the cosmos. It represents the thrilling tension between what we know and what we might one day discover. It teaches us to embrace the wonder of the unknown without surrendering our commitment to reason and evidence. It is a reminder that the universe is vast enough to hold wonders beyond our imagination, and that the most exciting phrase in science is not eureka, but that's funny. Whether this anomaly is ultimately filed away as a fascinating natural curiosity or becomes the first chapter in a new understanding of our place in the cosmos, its true value is already clear. It is a beacon that calls us to keep looking, to keep questioning, and to remain forever humbled and amazed by the strange and wonderful reality we are a part of. From the terrifying gravitational dance of supermassive black holes to the silent, frozen exile of rogue planets, the Mice Galaxies have revealed themselves to be more than just a collision. They are a comprehensive cosmic laboratory. Within this single, sprawling event, we find a microcosm of nearly every extreme phenomenon the universe has to offer. It's a place where the laws of physics are stretched to their limits, where destruction and creation are two sides of the same coin, and where the line between the known and the unknown is constantly being redrawn. We've witnessed the violent birth of superstar clusters in the depths of intergalactic space, the faint radio whisper of magnetic ghosts, and the profound mystery of dark matter clumps that challenge our most fundamental models. Each object, from the brilliant X-Ray Lobster to the delicate protoplanetary disk defying all odds, adds a unique thread to this rich tapestry, illustrating that the universe's capacity for wonder is truly limitless. This incredible diversity is what makes NGC 4676 such a priceless gift for astronomy. It is not a single experiment, but hundreds happening simultaneously, each offering a different key to understanding the forces that shape our cosmos. The chaotic environment of the merger accelerates processes that would take billions of years in a quiet galaxy, letting us observe in fast-forward the life cycles of stars, the growth of black holes, and the very evolution of galaxies themselves. The mice are a natural university, teaching us about gravity, magnetism, particle physics, and chemistry on a grand scale, all from a single, spectacular lecture. And our front row seat to this lecture is only getting better. The journey of discovery here is far from over. In many ways, it has just begun. The James Webb Space Telescope, with its unparalleled infrared vision, is already peering into the dusty hearts of starburst regions and analyzing the atmospheres of distant worlds, seeking answers to the questions its predecessors could only hint at. Soon, the next generation of giant ground-based telescopes, like the Extremely Large Telescope, will turn their massive eyes toward this cosmic dance. With resolutions previously unimaginable, they will track the individual motions of stars swirling around the central black holes, potentially witnessing the moment of their final merger and the resulting thunderclap of gravitational waves. They will dissect the chemical makeup of distant exoplanet atmospheres within the mice, and may even directly image Earth-sized worlds forming in those colossal debris disks. These observatories will transform the strange objects we've catalogued from points of light into richly detailed worlds, each with its own story to tell. The greatest discovery, however, might be the one we haven't even thought to look for yet. The history of astronomy tells us that every time we build a better window to the universe, we are blindsided by something entirely new and unexpected. The next great mystery is waiting within the data, a subtle anomaly that will force us to rewrite our textbooks once again. So we leave you with this question: which of these 30 strange objects captured your imagination the most? Was it the awesome power of the hypervelocity star, the profound mystery of the dark galaxy candidate, or the tantalizing possibility of Object 30? Let us know in the comments below. We love hearing what ignites your curiosity. If this journey into the deep cosmos fascinated you, be sure to subscribe and hit the notification bell, because we have many more deep dives into the universe's greatest mysteries coming your way. The universe is strange, beautiful, and endlessly surprising, and we can't wait to continue exploring it with you.